I would say, session where you have to understand a lot of things. It's just like a generic session. What you have to just understand the challenges. Like, okay, what is the different challenges when we are talking about the implementation point of view. Like in a semiconductor side, oh, if we are talking about the communication in a semiconductor, so most of the people in the outside world, like I'm not talking about the PhD, the people who are doing the PhD or the research scholars. I'm just talking about the undergraduates or maybe the MTech people. So they always have this confusion, like, okay, the communication and the VLSI and the embedded, and they always just talk in terms of like, okay, these are the three different fields. And I agree, there was a time when these three fields are basically the three different fields. So what I'm going to just do today, I'm just going to give you the little bit idea about the semiconductor side, and then we will. So Ashish already discussed with you in detail about the communication perspective, and then I'm going to talk a little bit about the integration of these two fields. So moving forward, uh, like how the integration is going to work, the complexity. So it's not like in a VLSI field, we are not doing anything with the communication side, and it's not like in a communication side. If someone is working in a communication side, they should not have any idea about the VLSI side, because when we are talking about the bigger picture is basically about the electronics. So everything comes under the electronics. I'm just talking in terms of the hardware perspective, from the circuit perspective. Even if you are saying like, okay, uh, from the software point of view also, yes, software is written in a, like in a language or some language. At the end of the day, you need some hardware where you're going to uh, just upload that particular software. So that means again, everything is going to be linked with the software. Sorry, that's a hardware. When we are talking about the communication, yes, in a communication, till the time things are there in the hardware, we can say like, okay, this is related to the electronics, and but once it will just go out of the hardware, like in our environment, I would say, then there are a lot of physics start playing a very important role, where we I'm sure like all of you know all those reflection, penetration. Then you have to consider all those things. So communication. So like you can see my from my degree point of view. So from the education point of view, I'm electrical electronics engineer. So I have an idea about the electrical also, the electronics also, and but when it comes to the master, that is more or less the communication side. But from the last several year, I'm working in VLSI domain. So I have pretty much, I would say, good understanding, or not the good understanding, or I will say that I have the basic understanding about both the fields, and that's just something I'm going to try to discuss with you. Just try to give you my perspective, like, okay, what are the different things you have to take care when when you're designing a communication device. So you have to just think from the VLSI point of view also. And if any one of you are from the VLSI side, then you think from the communication side also. So that's going to be the general topic of discussion today. I picked these three things: PDK, like physical design kit. We will discuss like, okay, what is the content. We will just go little bit in the deep also. Then we will discuss little bit about the packaging side also. Like, okay, what are the challenges in the packaging, and what uh, what is happening nowadays. So I will just take one of the packaging process. I will just explain you that thing just to give you an idea, like, okay, what are those things? And then in a VLSI point of view, when it comes to the implementation, then what are those implementation? How you're going to design your small chip? Those are the things I'm going to discuss mostly today. So this is the basic agenda which I have just figure out. Like, okay, this should be good enough for today talk. But yes, if anyone is interested, we can have a separate discussion later on. And but like I said in my the very first day, Ashish and Aditya, they are expert uh, when it comes to the communication side because they are working uh, on that side. So you can ask a lot of question to them also. So in the PDK side, we will discuss in terms of what exactly is a PDK and why it is important when I'm talking about from the quality check point of view. What is the quality I'm just talking about? And similarly, like I said, I'm going to discuss one of the packaging technique that is wafer level packaging. So I will just give you a little bit idea about what we are doing in the uh, low frequency and the high frequency side, and what are the challenges, what are the different packaging types are there. I will not go much in the detail, like in the depth side, because that will take a entire day. But yes, sorry, I will just give you a brief idea. Then yeah, this is the last one is my favorite one. Like, okay, in a semiconductor, how you're going to implement those things. So we are going to discuss that particular part. So before we start, if any one of you have anything for me, you can just let me know. So I'm not much comfortable with the this interface. I usually use the Zoom, but I will just see, like, okay, I think there are two sections. There is a Q&A section and there is a one chat section. Okay, I think let's talk about the
Sir, like we have disabled the chat section, so all the query will be in the Q&A section, sir.
great. Thank you.
Uh, Thank you, sir.
Yeah, so if you have any questions right now, before I start, then you, you can ask that particular thing. I think if you will, you guys will have a interactive session, then it will be good. Great. And I'm sure like Ashish and uh, Aditya is here. So they are going to support me. They are going to help me out when it comes to Q&A side. Okay, guys. So let's start. So first thing is, what is a PDK? So what is important in the PDK, and why we are talking about this the the PDK thing again and again, and what is the importance of the PDK? So basically, the PDK is mostly is a process design kit. So when I'm talking about the process design kit, so it's like there are three different words. One is a process. That means we are just talking about some process. Now that process that means that is related to something that is related with the foundry, because we are talking about from the manufacturing process. We are talking about the fabrication process. I would say it's a fabrication related things are there. So that means the foundry come into the picture when we are talking about the process. So all the rules, all the foundry related information supposed to be the part of this PDK, and that's the reason we are talking about the process. So the moment the process is going to change, the foundry will change, your PDK is going to change. Then we are talking about the design. Like now, when I'm talking about the design, that means using a particular foundry or for a particular foundry, I want to design something. Now that design can be your digital circuit, it can be your analog circuit, it can be your mixed signal circuit, or it can be just a small capacitor resistor. But the point is you want to design something and you want that uh, supposed to be fabricated by a particular foundry. So you n- need a very close integration. You have to work with those people very closely to understand like, okay, what is their requirement. And when I'm talking about a kit, it is just like a bunch of files, and that bunch of file someone is going to provide you, and that can help you to design whatever be the circuit you want to design. So if anyone is going to ask you like, okay, what is a process design kit? So what is a PDK? Because I'm sure when we are talking about any particular foundry, whenever we are talking about anything like, okay, we want to design it, we want to fabricate it, the first question everyone asks like, okay, do you have a PDK of that particular foundry? Do you have a PDK of 28 nanometer? Do you have a PDK of 180 nanometer? And then the second thing is, okay, is this PDK is TSMC specific, UMC specific, it's global foundry specific, or SCL specific? So then the next question we usually ask like, okay, first the technology node, then the foundry, like, okay, whether this thing is compatible with this that particular foundry or not. The third question we usually ask in terms of the tool which we are going to use to design our circuit, whether that tool is compatible with or support that particular PDK or not. So now you can understand what exactly I'm just talking about. Now I have raised three important thing in a PDK. One thing is a technology node, second thing is a foundry, and the third is basically I'm just talking about the tools. So it's just a bunch of files to model the fabrication process for the EDA tools. So if you are using a particular tool, let us suppose the Cadence tool, the open source tool, or maybe the Synopsys tool. So first of all, their tool should support a particular PDK. And if there is a mismatch, then that's not going to help you out. You cannot design using the PDK. Second thing is, if when I'm talking about the PDK, it should not be like, okay, you just take a PDK from the foundry, a TSMC foundry, and you just design everything, and then because of the cost issue, you can just talk to the SCL people and you just say like, okay, I want to fabricate this particular part. Then definitely they are going to ask you like, okay, have you used my PDK? So everywhere we are using this the terminology, the PDK, and every time when we are talking about the open source, when we are talking about the industry standard, when we are talking about a particular foundry, every time we are talking about the PDK. So it's very important before you jump to a conclusion, before you talk like, okay, I just want to start designing something, like, okay, which PDK, what is basically the PDK, what is the content in the PDK, what is the quality of the PDK. So we are going to discuss that part in a coming slide. So like I have mentioned here, this is created by the foundry, defining a certain technology variation for their process. So the important thing which is here, one second, let me just see. Yeah, this particular part. Yeah. So here the important thing is this process, this the technology variation which I'm just talking about. So when I'm talking about the technology process, that means one thing is technology node, and then I'm just talking about the variation also. So what is the variation in the technology node? So you can understand in this way, the final chip which is going to come after the fabrication is basically is going to be through some mechanical devices. There are going to be some machine, there are going to be some mechanical device is going to be there. And as we have the uh, significant digit, or you can say the precision of each and everything. Similarly, in our foundry also, there is always a precision related thing, like okay, this is going to support this much of part. Maybe if I can just draw something, I can just show you. So let us suppose, one second, the line. Yeah, this is good. Yeah. Okay, so I was just talking about, like okay, let us suppose you want to draw this particular structure. Now this is something which you are thinking, like okay, if this structure is basically, let us suppose 2 nanometer, is it something the foundry can precisely, accurately just draw this particular structure? So if this is with the help of a particular metal, let us suppose the metal one, can foundry design it, fabricate it with the exact 2 nanometer? So that is very important. So if foundry is not able to do it, then at least you're going to ask a foundry, like okay, can you tell me what is the percentage of variation? And if they will say, like okay, there is a some percentage, and that particular percentage is in terms of something like this, like okay, sorry. So if they are saying, like okay, they're going to be certain percentage, and that variation is going to be like this. So the inner one, you can see that inner one is basically the dimension which you were asking, like okay, this should be the dimension. But the external one is something which foundry is going to provide you after the fabrication. So if we will talk in that particular way, how foundry is going to provide you that particular information, how foundry is going to provide you this thing, like okay, I'm going to this is my precision. This is the something which uh, I would say. Come on, guys. Okay, yeah. So that particular portion, how the foundry is going to provide you, foundry is going to provide you that particular information using certain files, using certain data, and that particular files and the data which they will provide you, they will provide you in the form of I would say in some form, and that form, whatever that particular file or some document, that is going to be part of the physical design kit. That is the something, the foundry related thing. Second thing is, customer can enhance those PDK. So when I'm talking about the enhancement of the PDK, that doesn't mean you just the um, alter the data provided by the foundry. I'm just talking about you can add content in the PDK. So if you have a very good understanding about the process, if you have a good understanding about the design, so what you can do, you can add couple of more devices there. So let us suppose Foundry provided you 6 types of different capacitor. So they said, like okay, these are the capacitor which we are supporting, and these are the characteristics, these are the parameters which we have done for you. Now you can use these 6 type of capacitor in your design. So that means that is a that is just to support you, foundry provided you. So apart from whatever the process and all other things, they provided you this particular data also. But as a engineer, you're saying, like okay, I want to design my own capacitor. I just want to design my own inductor. I don't want to use these pre-designed devices, pre-designed capacitor and the inductor. So that means you can enhance the PDK, you can add, you can design. But yes, when you are going to do that particular part, then it should specific design style. It should be a specific design style. It should be there. So designer can use these PDK, they can simulate it, they can draw, they can verify the design, and they can do whatever the circuit they want to do it. Till the time all the rules and everything you are just following as per the foundry provided data, you're comfortable, you're okay. That means foundry, you know, like okay, this particular foundry is going to fabricate that particular this particular device or this particular design. They will fabricate those things. So back to the foundry, you will just provide this back to the foundry, and foundry is going to fabricate that thing, and they will just give you the final product. Now the question comes whether this final product is going to work or not. So who all are stakeholder? Who all are those people who those are like responsible whether this particular product is going to work or not? Who? So simple question. The simple thing is first whoever design the designers basically, so they design that particular product, yes, so they are responsible. Second thing is if it is not working properly, maybe the foundry, you can blame like okay, you design everything correctly, but it's a problem with the foundry because they were not able to fabricate it properly. So what foundry people are doing, they said like okay, we will provide you sufficient data so that tomorrow you should not come back and you should not say like okay, if your chip is not working, if your design is not working, that is because of my problem, because of my fabrication technique, because I'm going to provide you enough data which can help you in a designing process. And in that particular process, if you are saying like okay, you have verified, you have everything as per the data which I have provided, then I'm okay, I'm good, and there is going, I can give you the guarantee. Basically at the end of the day you need a guarantee from these people, everyone, you just need a guarantee. So the foundry said like okay, I will give you the guarantee. If something just messed up because of this particular part, what I'm going to do, I will refabricate, and that is going to be in a very not even, I'm not going to ask you any single money also, because at the end of the day everything is with respect to the cost. So this PDK, that's the reason this process design kit come into the picture. For Foundry is going to provide you a lot of data, lots and lots of data they will provide you. And then using that particular data, what you have to do, you have to design your circuit, you have to design your chip. And if once you will provide that particular design back to the foundry, then the foundry is going to verify whether you have done everything correctly or not. And if you miss anything, then they will tell you like okay, this is not the right thing. And that's the reason, if you know, like there is a one more terminology, is a mature node, and it's like it's still the foundry is working on that particular part. So when we are talking about the maturity, that means the foundry is they did everything, they verified everything, and then they said like okay, there is no problem. So in the news you will see like okay, foundry there is a company, they came up with a 2 nanometer chip, they came up with a 5 nanometer chip, and that's the first company they come up with the 2 nanometer chip. Maybe then the word will be there, and that particular 2 nanometer is working fine and without any issue uh, in a particular product also. So these are the two different things: fabrication something, and that fabricated chip is working correctly as per my expectation. These are the two different things, and that define that justify whether your chip, whether your node is a mature node or not. I'm not sure like how many of you know, but the foundries sometime they say like, okay, I'm not supporting this particular node, and they just skip a particular technology node also. So I don't remember the exact technology node, but I think there was 22 or 24 nanometer was there. One of the founder, they said, okay, I'm not going to, I'm going to just skip that particular part. Like TSMC, like Global Foundry, they came back sometime, I think 2 or 3 year back, and they said like, okay, my foundry is not going to support less than 7 nanometer, and they were facing some problem in the 5 nanometer, 2 nanometer. Intel had a foundry. They are also facing some problem in the lower technology node. What does it mean that they tried it? That doesn't mean that they haven't tried it. They tried it. They checked it, whatever the process. They did a lot of research in that particular side, but they figure out like, okay, whatever the final outcome, it's not as it desired one. Maybe they missed some parameters, some variation they missed in, because of that the chip is not working. So all those things matters a lot, and that reflect back in terms of the quality of the PDK. So we will discuss that particular part in the quality of PDK. What is that quality of PDK? Now let's see what are the different things you will get from the PDK. So always remember, whenever I'm just talking about the PDK, it is basically the first thing is from the foundry perspective. Like, okay, foundry is going to provide you a lot of details, lots and lots of details they will provide you. They will make sure like in insurance, like they have in a fine prints, they have at least 20-30 pages are there, and in a very small font size is a 9, and they will just give you that 20-30 pages, the bunch of a file. Similarly, if you will just go for the loan also, the same thing is going to happen there also. Similarly, the founder is also going to provide you a lot of information. Like, okay, they will give you a document of maybe the 1,000 page. So, and in that 1,000 page, they will just mention each and everything. Then after that, within that 1,000 page, maybe somewhere they just mark it as a asterisk, and then in a one of the line they will say like, okay, for this type of thing, refer this document, and that document itself has a maybe the 1,000 page. That means there are they want to make sure like, okay, if something messed up, at least you are not going to sue them, or you are not going to tell them like, okay, this is your problem. So that's a foundry related thing. So they the way they provide you. So here, if you will see design rule manual, so they will provide you a lot of design rule manual, like, okay, you have to just follow these things. So I have couple of 4 or 5 slides where I'm going to give you like some design rules, some different type of design rules, which they are going to provide you. So design rules plus verification deck also. So not the verification deck. So forget about the verification deck, but yes, this design rule I'm just talking about. So the founder is going to provide you all these design rule manual. And when I'm talking about the manual, everything is documented in the form of a PDF. It's not like they will just give you some anything else. That means you have to understand the PDF. You have to understand like, okay, what exactly is the meaning of that particular one line or the two line. Worked with the uh, uh, two foundries very closely. Not the two foundries, basically the three foundries very closely: the Global Foundry, the Samsung Foundry, and the TSMC Foundry. And so my one of my job role is just to read their manual, just to understand what exactly they are talking about from the process point of view. And there are a couple of technology files. So those technology file I have to sometime in I have to design, I have to code those technology file, and sometime it is like I have to verify whether that is something we are supporting or not. So I know the pain and the language, and just to understand the process, sometimes it's you cannot directly understand just by reading a one line. For that, you need a pictorial support also, and that pictorial support is not like, okay, just the the one view like in a 2D views is sufficient. It's just like you have to imagine, you have to visualize the 3D view of that particular rule also. And for that, you should know like, okay, what is the front view, what is the top view, what is the cross section view, what is the bottom view, what is the side view. So all those things you have to understand those things. So that's one of the thing as a foundry related thing. Now the second thing come, which I haven't discussed in the previous slide, that is the EDA companies. So it's basically the EDA tools, I would say. So these are the companies, they provide you the tool like the Cadence, Synopsys. There are a lot of open source we are using. So when I'm talking about the EDA vendors, when I'm talking about the EDA companies, what exactly they are doing, their job role is to provide you tools. And when I'm talking about the tools in the backend, basically in the layman language, I can see the softwares. Within those softwares, you can design the schematic, you can design the layout, you can do a lot of simulations, you can verify. If you're saying like, okay, foundry is providing you certain design rules, so how you're going to verify that particular part? If they are saying 2 nanometer, the distance, the width of a metal wire supposed to be the 2 nanometer. Now how you're going to verify that thing? There is no scale in the market which you can use and just measure, just say like, okay, 2 nanometer this thing. So what you have to do, you have to use a tool. Within that particular tool, you will just draw a line and maybe the some shape. Then you're going to zoom in, and once you're going to zoom in, and then you will say like, okay, the scale which is provided by that particular tool, you will use that particular scale and see like, okay, whether it's a 2 nanometer or not. And on the basis of that, you are going to verify like, okay, whatever with the rules foundry provided you, like, okay, there should be a minimum distance between two metal layers, and that minimum distance may be some 1 nanometer, 2 nanometer, maybe 1.5 nanometer. And then that minimum distance, they are going to provide you, the foundry is going to provide you the 10 different rules for the spacing rules, I would say. Now, in your design, you cannot manually check everything. Just go structure by structure everywhere and just check it like, okay, whether things are working correctly or not, whether you have designed everything correctly or not. So what you have to do, you have to use these tools. These are basically the automated tools. They are going to do the verification for you. And once they are going to do the verification, they will tell you like, okay, where is the problem? So that verification process, which they are going to do, how they are going to do that particular verification process. So if I'm talking about the cadence, how they are going to do the verification on your behalf and as per the foundry requirement. So they are going to use this documentation, whatever the documentation foundry provided, then they will write certain rule decks. So these are the rule decks I'm just talking about. They will write certain rule deck. So it is going to be some file is going to be there. So they are going to give you a rule deck, and that particular rule deck they will use while you're going to do the verification. While you're saying like, okay, I just want to check whether I am following the foundry design rules properly or not. So from that perspective, you're going to run those rule decks. Now these rule decks basically, now you can see like, what is this rule deck? They are going to write the whatever is written here in a language, in a file, in a format is which can be understandable, easily understandable by their tool. So the important thing is by their tool. That means if Cadence is going to write a deck, so Cadence know, or maybe their software is understand a particular language because they have written in that particular way, or the person who's going to write the software, they are saying, okay, if the spacing is written, that means the spacing keyword is a spacing, that means I'm going to understand like, okay, this is a spacing rule. Maybe the synopsis is saying like, okay, I don't need a spacing, even if the space is written, I can understand like, okay, this is a spacing thing. Maybe as a free maybe some other foundry, not the some other foundry, maybe some other maybe some other uh, EDA vendor, they will say like, okay, I'm going to do it. Am I audible or?
Yes, sir, you're audible. Audible, sir.
Okay, okay. Because just right now, someone's saying like, okay, some other voice is coming. Okay, so I was just talking about in terms of the some other the tool provider. Maybe that particular tool provider, they are going to they are going to uh, do it in a different way. Like they will just write it. They will say like, okay, S means it's a spacing rule. So that means these rule deck these rule decks are basically written by anyone, or maybe you can say originally it's supposed to be written by the EDA vendors, but but they should make sure like, okay, they are compatible with the foundry people. So what is happening between those two companies, like the EDA vendors and the foundry? They work very closely with each other, and they say like, okay, foundry is saying like, okay, this is my new rule, and cadence is saying, okay, I implemented that particular part, I have coded this thing in my rule deck. Now, EDA vendors also don't want like tomorrow you just come and you just go and just say like, okay, it's because of you my chip is not working. So what they will do, they will work with the foundry very closely, and they will say like, okay, these rule decks is certified by the foundry. And once that rule decks are certified, that means foundry checked it. Like, okay, this rule deck is as per my process. The foundry, once the foundry is going to do that particular part, now it's a certified deck. Now that certified deck, anyone can provide you. So as a designer, you can ask these certified decks from the EDA vendors also, or you can ask these certified deck from the foundry also. So it's a very confusing thing. A lot of people, even in the VLSI industry, they have a lot of confusion. Like, okay, who's going to provide you this particular PDK? But now you can imagine, like, okay, anyone can provide you. So if TSMC is supporting cadence, means they know like, okay, my 5 nanometer, the 2 nanometer process, and the TS and the cadence, the deck that is certified, TSMC can also provide. Similarly, when it comes to the cadence, they can also provide you the same PDK, and they can say like, okay, we are the certified vendor of TSMC 2 nanometer PDK. You can also take this particular PDK from me. So now it depends, as a designer, as a company, uh, whether you got a good deal from the EDA vendors or the TSMC. Maybe TSMC can say like, okay, this is my foundry, and if you are going to promise me like, okay, you're going to fabricate using my foundry, then I can give you the free PDK, because they are seeing the business, because there is a competition. The global foundry is there, so they don't want to lose that particular part. And now you have a choice whether you want to go with the synopsis or the cadence. So what cadence is saying, like, okay, if you are using my tool, I can provide you the free PDK, I can provide you that particular part. So you need a TSMC or you need a global foundry. We are certified with the both the foundries. Now it depends on you, like, okay, where exactly you're getting a good deal, and what exactly you want to do it. So that means till now two things are clear. First thing is what exactly the foundry is going to provide you. So they are going to provide you mainly they are going to provide you the design rule manual. The second thing is this verification deck, supposed to be provided by the EDA vendors, but yes, because they are going to work with each other very closely, anyone can provide you if they are the certified things. Now from the EDA vendors point of view, this is the rule deck, this is a verification part. The second, after, there is a one more thing, and that particular thing is you are going to use a particular tool to design a particular resistor. and let us suppose you're designing a resistor or the capacitor or the inductor, anything you are going to design using the some metal 1, metal 2, metal 3, these layers. You want to use these layers, metal layers, within your semiconductor side, and you are saying like, okay, I'm going to design this particular part. Now when I said layers, what is the meaning of the layers? When I'm saying layer name, metal 1, metal 2, metal 3, this basically is a layer name. When I'm talking about what is the purpose of M1, what is the purpose of the different layers? So these purpose, these layers, when we are talking about the physically, so here let us suppose if I will draw something, what is the meaning of this, and what is the meaning of this thing? So one is a check, one is a cross check, one is a normal one. Maybe what I can say like, okay, I have a another layer, and that layer is with a red color. So this is the way I can differentiate. I can say like, okay, this is these are the two different layers. Now what is the purpose of these two layers? How these two layers are going to be uh, understandable, like, okay, how you can understand like, okay, which one is a metal one, which one is a metal two, how the foundry is going to understand that particular part. So all these details you need somewhere, and that is that portion which I'm just talking about, like, okay, you need all these details. So if you need all these details, so for that particular part, our technology data come into the picture. And here in the technology data you can see, I'm just talking about in terms of the layers, the colors, the display attributes. I'm just talking about the electrical rules. So that means technology related data. So there are two portions of the technology related data. One is as per the EDA vendor, whatever be the rules and all those things. Second thing is, if EDA vendor is saying it's a metal one, how the foundry is going to understand, okay, this is a metal one. So that means again, foundry is going to provide you certain information. So usually they provide in the form of a GDS layer, because they are saying like, okay, this is going to be the GDS database I need. And in the GDS database, if it is written 61, that means if it is related to the metal one. And so what of EDA vendors, they can say like, okay, in my tool I'm saying 21 is a metal one. So that means in the tool it is a 21, in a foundry side it is a 61. Now how you're going to map these two things? So there are going to be a certain mapping files are also there. So all those things is basically related to the technology data. Again, this is going to be part of your PDK, because that doesn't make sense if someone is going to write all these things. So you need this thing as a part of a tool. You need all these things as a part of your before you start designing, because then only you will be able to understand like, okay, if you're drawing a particular layer that is related to the metal one or metal two. And that's a thing where this the database related thing come into the picture. The cadence design, if you just download it, save it, you cannot just upload in a synopsis tools directly. Either you have to just remap it, you have to just make sure like, okay, that is compatible. That So there are two things. One is the data format, another thing is even if the data format is same, whether all these layers, numbers and all those things, those are different, or those are the same one. So you have to understand that particular part also. So these two things, these three things, I just gave you an idea about the verification deck, technology data, and the design rule manual. Now these three things, I will just finish it. These three remaining three things very fast, and then after that, I will just ask you the questions. Like, okay, if you have any questions. So these three things, where I'm just talking about the model files, when I'm talking about certain symbols, device parameters, pieces, these are something as a add-on basically for you. Foundry is saying like, okay, I'm giving you certain capacitor, I'm giving you certain resistor, like I gave you an example. So you can also design that particular part, but I'm just giving you that particular thing, and I'm doing that particular work for you. And once I'm going to do that work for you, at least you can use these things uh, uh, directly. So you're not supposed to redesign everything, re-verify everything, and just check whether what is going to be the parameters of those things. You're not supposed to simulate those things. You're not supposed to characterize all those particular parts. So as a add-on, I'm providing you that particular data. And who can provide you? Maybe Cadence can also provide you, or maybe the Foundry can also provide you. And that's something you can also design yourself. So I'm just checking in the Q&A session. Someone just asked, like, okay, what is the meaning of the enhancement in the PDK by the customer? So this is the portion I'm just talking about, enhancement of in the PDK by the customer. So you have two capacitor design. Maybe you can come up, you can say like, okay, this is my new capacitor design. So this is the area where I'm just talking in terms of the research. Maybe the colleges, universities, they are doing a lot of research, and they are saying like, okay, for the TSMC, for Cadence tool, I simulated this thing. I am following all the design rules. I am following everything, but the performance of my capacitor is far better than the other capacitor, other known capacitor. That's the place a lot of research is going on. People are talking about in terms of the different processes. They are talking not the process. Basically, the process is as per the foundry. They are talking about the different ways to design the capacitor. They are coming up with the different ways to design the resistor, inductor. So couple of ways, like how the inductor is going to be designed. So I have a couple of slides where I'm going to give you like, okay, what are the challenges in the nowadays in the 5G especially, and what people are doing, and whether what type of designs they are talking about, what are the advantage and the disadvantage of those things. I'm going to discuss that particular part. So those things are basically the research related things, so you can enhance that particular part. From the process point of view, there are CMOS, there is BiCMOS. If you remember, in the very first day, we were just talking about not only the silicon, there are the different material we can use it. So if the foundry is uh, like like the foundry is uh, know very well about the BJT. They can design it, they can fabricate it, the BJT based devices, they can fabricate the MOS based devices. So what you can do, you can say like, okay, I'm just working on the I came up with the something which is a BJT specific, and it is far better than the CMOS. Then what is the problem? You can come up and you can say like, okay, this is the something I just want to add as a part of my the process. So that's something as a add-on. So yeah, so that's we will discuss couple of more slides. Okay, just to give you an idea what is in a PDK. But before that, let me just check few of you just asking couple of questions. So I think someone asked Aditya Kumar, which file provide the layer information? Yeah, it's a technology file. There are layer information you can get in the technology file, and depending upon in a design which stage you are working on, the basis of that you will see like, okay, different tools are going to capture this information in a different files. But normally if you just go and just search the technology file, you will get it. That is it can be if you're talking about the interconnect related thing, then it's going to be the interconnect technology file. If you're talking about in general, there is a .tf files. So you can check that particular part. Gaurav is asking, is ADS provide any free PDK which is compatible with the design rule of the foundry? So I think you by now you should have your answer. So you're talking about the two things, free PDK, and you're talking about the design rules of the foundry. So if you are talking about the TSMC, if you are talking about the TSMC, then are you talking about the free PDK of TSMC? So if that is the case, you have to check TSMC. If you're talking about the free PDK, then you have to see like, okay, which particular foundry is supporting that free PDK. So recently, like Google released certain PDK and they say like, okay, it's a free PDK. Maybe there is a couple of other providers, they are saying the free PDK. Now, free PDK with the some cadence specific free PDK they are providing you. So now question come, what exactly, whether a particular PDK help you to design, simulate, and do the experiment, or whether that particular PDK you want to use for the fabrication thing also. That means you want to fabricate using that particular PDK also. So in the market right now, so in the current market, there are basically you will see three type of PDK. One is the PDK which is foundry specific PDK. That means if you have that particular PDK and you can fabricate your design. That means if whatever be the design you did it using that particular PDK, like the TSMC specific PDK, if I'm talking about, you can do everything, and after that, you can just go to the TSMC. You can say like, okay, I want to fabricate this particular part. That's the one type of PDK. Second thing is a general PDK. So that's general PDK when I'm talking about. So that's not going to help you in terms of the fabrication process. But like Cadence or the Synopsys, they usually provide you certain general PDK. So in a Cadence, it is a GPDK. In a similar in a Synopsys also, they have certain Synopsys specific PDK. Uh, uh, so uh, so that name, I think. I just missed that particular name, but yes, they are also provide you certain PDK. So in that PDK, what can happen if you have Cadence tool or the Synopsys tool? So their general PDK, using those particular PDK, you can design a layout, or you can design a circuit, you can do the experiment, you can do the simulation, you can do everything within the Cadence tool. But that's a generic PDK. That's not specific to a particular foundry. You cannot convert that design into a fabrication side. So what they are going to do, maybe they are just going to changes certain values. So their tool is compatible with that particular PDK, but you cannot fabricate those things. So if you have a Cadence tool, if you have the Synopsys tool, then you will see like, okay, usually in an educational institute, they usually provide the general PDK so that you can do it for your research work. You can use those PDK for your research work. You can do everything, but you cannot come up with the fabrication related thing. Then the third concept is basically the free PDK, which people are asking. That free PDK, there are a couple of foundries. They said like, okay, I have few free PDK maybe for the higher technology node, and I'm just providing you free of cost. You just do it everything, and once you will come back, then I'm going to help you to fabrication. Now that free PDK again, whether that free PDK is compatible with the open source tools, or you can say the free tools, or that is compatible with the Cadence Synopsys, that again a matter of question. That's again a question. Like, okay, whether that's working, that's what about that particular PDK? Now, if you're using a open source tool, if you're using a free PDK, or you can say if you're using a open source PDK, that means you can tweak, you can change tool also. That means you can make certain changes as per the PDK requirement, or it's easy to make changes in the PDK open source PDK, that means you can just make certain changes as per the requirement. So at least you know, like, okay, this particular open source PDK is there. If I will just make these changes, not the values I'm talking about. I'm not talking about in terms of the values. I'm just talking about in terms of the syntax and all those things. So maybe you can just make those changes and you can do your experiment. So that's a part of the different classification, I would say. So this is something which is my version. Like, okay, there are three different type of PDKs. Now, Manish was asking, is possible to use the file to structure proposed in the TCAD for design circuit and a cadence? I think I already gave you an answer. So if you have a good understanding, you can do that particular part. Open source EDA tool which can make use of a PDK supplies by the foundries. Yes, so it's an open source tool. So you have to check it whether your open source tool is compatible with respect to which particular PDK of the foundry. Like maybe once you're going to download a open source tool, usually they mention like, okay, my tool is uh, going to work with the XFAB or maybe some higher technology node. So even in the open source tool also, in some version they will mention in a note like, okay, this version is changed or the tweaked or the compatible with the 180 nanometer 90 nanometer. So with the 90 nanometer open source tool, if you are thinking like, okay, you can design something with the 45 nanometer, you cannot do that particular part because maybe means you can do it, but obviously you will not get the correct result. And also you have to just check it which particular PDK they are talking about. So in an open source tool, they will give you a one version of PDK, and that is a their own version. Maybe they tweaked. That is again the general PDK they will provide you so that you can use their open source tool. But that general PDK is written around um, certain foundry, and you have to check that particular part, like, okay, which particular foundry they are referring. How do you define the term technology node for the different semiconductor devices? So it's basically so if I'm talking about the channel in terms of the BJT and in terms of the MOSFET, basically the technology node. So nowadays we are talking about the technology node in the MOSFET devices, and that's we are using it the channel length. On the basis of that, we are defining that particular part. Now in the diode and the BJT, mm, there. Okay, so again, that is again we are talking in terms of uh, the channel length only, but no, not exactly the channel length because there is nothing like that. So, Wasim, I'm not sure because even I have to check that particular part, like in a BJT, whether there is a concept of the technology node or not. Obviously, it should be there, but how they define it, I don't know. Because when I entered into the industry, by that time, the BJT was like we were not using the BJT. So my mostly I worked in a diesel side, and the diesel side, everyone moved in a MOSFET side. So I have a good idea about that particular part. I never thought even in terms of the BJT also. But that's a good question, I would say. Okay. So anyone else have any other question? I know like till now it become very uh, heavy one, but next couple of slides will be like I will just move very fast. Okay. Anyone else have any other question? I don't know like whether you guys are getting some information or not. Oh, great. So Ashish or maybe if Aditya is here, maybe if you want to add something, Ashish, till this point. Ashish, sorry, we
Just
can't hear.
getting up. Okay, wait. Now, am I audible?
Yes, yes, you're audible now.
Yeah. Okay. So, till now, you have given a, I think, very good, fair idea about the PDK. Okay. So, I think participant, even I got to know many new things. So I think you are going good for this. And if anyone has any doubt regarding VLSI also, okay, so he is expert in VLSI domain, so you can ask question from that domain also. So that's my side. So you can go ahead.
Yeah, thanks, Ashish. So the reason I ask you because this is your audience. These are basically you're just dealing with these people from the last 4 days, so you know very well all of them. Okay, so okay, someone just asked some question. What is that? What is the term DSMC? Uh, I don't know. Maybe so. You yourself just mentioned like okay, it is. I think so. Uh, I think even I think I don't know. So once you will come up with a, uh, I mentioned DSMC. Oh, no, so it's not a DSMC. It is a TSMC. So let me just write TSMC. So it's a foundry basically. So when I'm just talking about the foundry part, so that's just something. Uh, I'm just talking about TSMC. So that's TSMC I'm just talking about. Anything to do with the PDK? Sir, is the reference of my above question how to proceed to for using my TK design structure for circuit designing in the cadence? Just give me guys just 1 minute. You just give me. Okay, so okay, so you're asking about Manish. You're asking how to generate PDK for the TK design structure. So Manish, simple answer and the complex one also. So if you don't want to fabricate anything, like I'm just talking about from the fabrication point of view. If you don't want to fabricate anything, then you should have a understanding about the tool. And if you have understanding about the tool, then you can do anything. So if you want to write your own PDK, you should first understand what process you're talking about. So for the cadence tool, let us suppose if you're talking about for the cadence tool, irrespective of whether it is uh, uh, a particular simulation related thing or with respect to a particular portion. So I would say best way if you have any other PDK from the cadence, you just understand that particular part, their syntax, and then you can just make certain changes. You can do in that particular way. So there is no other way because that's a cadence specific tool. So you cannot write anything which is compatible with the cadence until and unless you know how cadence tools are going to work on a particular file, how they understand the particular rules. Yes, there are couple of files, there are couple of rule decks, there are couple of data, which is IEEE standard. That means their syntax and everything is already um, standardized by the IEEE. That means if you will write anything within that particular format, even the cadence synopsis, even the freeware tool, they can also understand. So again, it depends at which stage what exactly you want to do, then you can make all those changes. But yes, uh, maybe Manish, what we can do, we can discuss once again, maybe offline, like okay, what exactly you want to do. If you just want to write your own PDK, what exactly you want to do. So I have couple of slides, and that can help you to understand, like okay, if I'm talking about writing or creating my own PDK, then what are the different checks are there, and what are the different things I have to follow. So maybe after that particular set, you will have a general idea, like okay, how each and every PDK has a dependency over the tool also, and how many tools. It's not like only one tool. When I'm saying the tool, that means maybe in the whole process there are 5, 6, 10 tools are there. So maybe you have to do in that particular way. What the result will give in the LVS is a layout versus schematic, and then again it is basically the verification deck. So whenever we are talking about the verification, that means you are validating something, whether you are following particular rules or not. Or you can say you're checking two things. One is a golden, one is a, or you can say the reference, and another thing is whatever be your design or maybe the your things. So when we are talking about the layout versus schematic, so what is happening most of the time, you guys, when we are doing this simulation and everything, we do with the help of the schematic. So schematic in the sense, the symbol is going to be there, and the schematic structure is going to be there, and on the basis of that you will just do the simulation and everything. But in the designing, in the VLSI designing, when we are going to talk about the layout, you have to just check it whether your layout is as it is, or whether that layout is as per your schematic or not. So to do that particular checking, it is a layout versus schematic. So I will discuss all those things in a couple of other slides. Let me just go through, and then maybe we will come back to this particular part. So like schematic symbol. So now I'm just finishing up all these PDK thing little bit one by one, and because I took a lot of time just to explaining the PDK portion, and then I will come back, and then I will check all of your questions. So I think yeah. So last question, I'm just talking about the Anupam Anand. After that, I will check every question. Now this is a basically the schematic symbol. So this is I'm trying to show you, like okay, in what form you will get the PDK. So this symbol you will see. So you will find this symbol in your PDK also. So that means when you are going to use your schematic tool, within that schematic tool, so you can see, like okay, by the with the help of, there are couple of NMOS, PMOS, those are pre-designed. You just drag, drop, and you say like, okay, this is my PMOS, this is my NMOS. And so that schematic I'm just talking about, someone designed it. Who is going to design it? Maybe the foundry, or maybe the someone is going to design it. That is a part of your PDK. So that is the PDK I'm just talking about. Now, symbol is nothing like, it's not like you can say like, okay, there are 1, 2, 3, 4, 5, 6, 7, 8 lines are there. No, it's not only the lines. Lines are basically the pictorial presentation. But what is happening in this particular MOS, these are couple of parameters. So all of us know very well simulation, you're going to do the simulation. So all of us are engineers, or maybe the masters, we are doing day in day out, we are just talking about in terms of the equations. Now when you're talking about the equations, that means in the books and everywhere we are talking about the equations, and those equations, once we will put the values, then we will get the output. So there are certain inputs, there are certain constants are there, and then you will get certain output. Like okay, if I want to create the current which is passing through this particular MOS, so there are going to be, I think, different parameters are going to be there. And then the concept of this uh, the model file come into the picture. So there is another model thing. So if you will see, there are standard models like BSIM 1, 2, 3, 4. Nowadays we are just talking about I think the BSIM 4 point some version, or the 5 version. So what is this BSIM thing? It's basically the order. We are talking about the equation order, the first order, second order, third order. Think from that particular perspective. So when I'm talking about the order, doesn't mean the same thing. But yes, in your a semiconductor industry, in the simulation side, you will see there is a very small equation also, V equals to IR, which is very linear equation, and you can just use it and you can just simulate it. That's good. But the moment your resistor is going to change with the current, that means, or you can say right now we are saying V equals to IR. We are saying, okay, if I is constant, there is a direct relationship between the V and R. But there may be a certain scenarios where I has a relationship with the R. That means if you will change the V, your I will also change and your R will also change. And I will change with respect to the R also. So there may be some relationship with respect to that. That means now I'm just talking about the complexity. There may be some other parameters also. Maybe that particular parameter, if you will change, it will affect your I also, it will affect your R also. And that I and R, the way it is going to change, it is going to change in a very different way. In a different way, in the sense, in a different scaling factor, different proportion, I'm just talking about. So like in a non-linear devices, when we are talking about, so that means non-linearity we are talking about. Now how you're going to tell the tool, like, okay, do the simulation on these particular part. So these models, when we are talking about the models, so that model is basically, we are going to talk about like on a BSIM4 model. There are going to be a big equation, and that particular big equation will have 50 parameters, 50 standard parameters. And there are a couple of other variables which we have to give as a input. So like here, length, width, these are the parameters which you will change, and your simulation is going to change. Now if you are going to do the simulation with the bsim1, then you will get the different result. Bsim2, you will get the different result. 3 4, you will get the different result. And what are those 3 4 parameters? I will just show you, like, okay, what are the list of the four parameters. So what you can do, you can just go back and just search bsim4 spice models, and then you will see for each and every I would say the component, like like if you are talking about the resistor, if you are talking about the capacitor, whether it's a MOS capacitor, whether it's a MIM capacitor, when we are talking about the NMOS, when we are talking about the different type of NMOS, we are talking about the PMOS, different type of PMOS. Everywhere what they are doing, they are modeling this NMOS and the PMOS, and modeling in the sense they're giving you all those variables, and they will give you like, okay, this particular variable have this much of constant value. So that constant value is a part of that spice modeling file, or I will say the bsim model file. And foundry is going to provide you like, okay, my MOS is related to this particular model. These are the predefined variables. So as the foundry is going to change, as your process is going to change, these variables are going to change, and that's the something foundry is going to provide you. So now when I'm talking about the schematic symbol, so this is basically a schematic symbol, and here you can make the changes. It will help the tool to understand like, okay, you made the certain changes, and these symbols has internally, they are mapped with a certain models basically. And when you are going to do the simulation, is going to help in that particular perspective. Now P cells is like, again, you predefined couple of cells when I'm talking about the layout. So now the layout itself is designed by someone for you, so that you're not supposed to design again and again. So it's a parametric cells. Basically, P cells is it's not like AND gate, NAND gate cells. We are talking about the parametric cells. So basically, I fixed a couple of parameters, and I said like, okay, these parameters, with this parameter, I already created the layout, the symbol, everything for you. What you have to do, you can just use that particular part as it is. So MOSFET, if I'm talking about a PMOS, if I'm talking about a NMOS, so you can design, you can, from the layout perspective, you can design, you can say, okay, this is my weight, this is the different layers. That is the one way. The second way is, I will give you everything ready. I will say like, okay, if there are 10 different type of MOS, I design it, characterize it, everything, the symbol, and the piece cell also. That means the layout also. What you have to do, you have to just drag and drop the way you are doing for the schematic. Similarly, you can just do for the your layout also. Just drag and drop, just place it. That means it's done. Everything is done for that particular part. You're not supposed to touch those things. Those are verified as per the foundry requirement, because we know these are the basic building blocks which anyways you need it. So if you need a particular PMOS, then why every time you need a you're supposed to design that particular part? No need of do that particular thing. You can use PMOS specific things. So that is a part of your uh, I would say the PDK. Then rule decks. So like I said, rule decks is going to be coded in a certain languages, and what we are talking about, we are just talking about certain rules, and these things, this pictorial view, it will come from the foundry vendors, whatever with the EDA vendors, they coded in this particular way. When I'm talking about the LVS, it's basically layout versus schematic. It will give you a certain deck also. That means how to compare, how to just compare the layout and what's those things. So these, I'm sure, like, okay, you cannot read all these files right now, but the reason I just gave you the snapshot just to give you an idea, like, okay, this is a something, is a English in an English language. That means you can understand, like, okay, it's written here database precision thousands. Now if you know what is a database precision thousand, what is the meaning of this thing at this particular place, that means you know, like, okay, how to write it and how to read it and how the tool is going to do all those things. So this is basically in the form of the ASCII file. Now, similarly, the extraction data also. So now when we are talking about the extraction data, so what is the extraction data? So it's like there are two metals, and if you want to understand what is a resistor of those two metals and what is the capacitance between those two metals, and if I'm talking about a particular PMOS device, basically, so it depends, like, okay, what exactly I'm just referring to. In a PMOS, you know, like, okay, there are internal capacitance, there are internal device capacitance I'm just talking about. So am I going to give you that particular data or not? Yes, I have to give you. If I'm giving you a particular P cell, then I'm doing all the simulations, everything is doing, but maybe somewhere you need a input cap and an output cap. You may need certain CGD, CGS, all these numbers. So I'm going to provide you that particular part. And then again, it depends, like, okay, in terms of the order also, whether I'm just giving you a lumped capacitance or I'm just talking about the distributed capacitance. So all those things is a part of your parasitic data. Sometime what happen, just to make your life more easy, uh, EDA vendors in the foundry, they will give you certain parasitic related informations in the metal layers also. So what they will do, they will create a dummy structures, and for those dummy structure, they will tell you, like, okay, these are the parasitics. So that is a different whole flow itself, but again, that has a relationship with your EDA tool also. So in a EDA tool, one way is you tell the tool, like, okay, do the extraction from the scratch. That means whatever with their algorithm, whatever the uh, the 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 way they calculate the capacitance, they are going to do from the scratch, but that takes a lot of time. Then there is another concept which is a pattern matching. So now for the pattern matching, that means what the tool is going to do, it will check your design and it will check the pattern, and it will say, like, okay, this design is this particular, the portion of your design is matching 99% of this particular pattern. Now what is that, this particular pattern, someone is going to give you that particular pattern also, and that pattern is basically the part of your the PDK. So what I'm going to do, I will, as a foundry or maybe as a vendor, I'm going to create a patterns, and for that particular pattern, I will give you all the capacitance related information. So it is basically, now it become a lookup table. So there may be a thousands of pattern, and each pattern has a capacitance and the resistance. Now what the tool is has to do, tool has to just map your design with those set of patterns. And if maybe you can just set within the tool, like okay, 90% if it is matching, just give me the cap and the rest value. So what they will do, they will just match it and they will tell you like, okay, this is the capacitance, this is the resistance value. So it's very straightforward. They will do that particular part irrespective of, you just tell the tool like, okay, calculate the capacitance using all the formula and all the techniques, and just tell me like, okay, what is the final capacitance. Then the capacitance is going to calculate it with the algorithm, like okay, that C equals to epsilon A by D, then A is a delta A, D is a delta D, and all those things will come like you have done in your trigonometry, not the trigonometry. I think in your physics you have done all those integration and differentiation related thing. Yes, so that's something is going to happen in your in the back end of the tool. So we usually talk about like in a field solver. That means it will go into the field and it will solve it. And there is a something like the pattern based extraction tool. That means it will just match the pattern and it will just give you the result. So that is also the part of your those patterns respective capacitance, that is also a part of your extraction rules also. Then layer numbers and the technology file, like someone was asking about the technology file. So this is the technology file and these are the layer. You can see like, okay, ND. Now what is ND? N type diffusion I'm just talking about. So maybe in one tool N is a N type diffusion. In some places it's written NDIFF. That means that is a N type diffusion. In some places it is written as a N diff in a small letter. In some places it's written as a n diff as a capital letter. Then what is the color of that particular layer? So those things, this particular information, this is a pictorial information, and this information is going to be present as a part of your display file. So there is a display file also, and then there is a technology file. So here also depends like, okay, how people are going to code it. So like here, if you will see in this particular snapshot, there is a color syntax is there. That means whatever be the shape I'm just talking about, the metal I'm just talking about, I'm just talking about from the color point of view. This is the color. This is the GDS number. Remember, I was just talking about the GDS number. I'm just talking about the GDS data type. I'm just talking about in terms of the edge layer, whether it's a part of a particular, you're going to use it as a part of your edge of your design. What is the angle? What is the width? What is the spacing? All those things you're going to mention in this particular technology file. This is the model file which I was just talking about, right? Like you can see here, it is a BSIM 4.6. So if you will see here, model P1 PMOS level 14. So now I'm just talking about the PMOS. The name of that particular model is a P1, and these are all the variables, not the variable that those constant values I'm just talking about. Now constant values in the sense, now if I can tell you, maybe you can figure out couple of things. Like here you can see TOX, thickness of oxide, TOXP. Now what is this PEM? So you can say like, okay, sorry, E, P and M. Yeah, here. So they have different values. So that means we are talking about the thickness of the oxide. Now what type of oxide, where exactly this oxide we are using? So on the basis of that, whether it is a side one, it's a top one, it's related to the PMOS, it's related to the some other oxide. So we are just talking about like, okay, what is their thickness? So these thickness are there. So this is the process specific information, because the foundry is going to fabricate with this particular thickness. So if you are going to use a P1 type of PMOS, they are going to use these parameters in their fabrication side. So they are not giving you the control, like, okay, you cannot change the thickness, but and if you're not changing the thickness, then how the simulation tool is going to simulate it? Because in the simulation tool, that equation, that number is there. How that number is there? This number is going to be provided by this model card. So we usually talk about the model card of a PMOS. There are couple of other things. Maybe I can just figure out if I can tell you in terms of which you can easily understand. Like here you can see VTH 0. So VTH is basically the threshold voltage. Now I'm just talking about there are one threshold voltage which is basically the 0 1, the by default in a particular temperature, the Kelvin temperature we are talking about. So this is the VTH. This is a V saturation. So we are talking about the V saturation. We are talking about the LOD VDH. So um, I'm not sure, like, okay, how many of you know this particular part, like, but the length of LOD and then VTH we are talking about, the width we are talking about the lambda. So here we are talking about, like, okay, this is going to be my lambda. So all these things, if you will go back and if you will just see your book, and if you will see all those parameters, so what you can do just to understand the this particular bsim model files, if you will go with a with a some basic book, first go with the basic book and just go with the bsim 1 and then try to map it. So whatever be in the equation, whatever they have mentioned 2 or 3 constant values, that you can easily correlate with your bsim 1, then go with the next level of modeling. So in that particular, I forget book, couple of books. Maybe when I was in engineering, then I did it. So there are couple of semiconductor related books, and those are hardcore semiconductor related, where they are just talking about in terms of the MOSFET, the current. Then they are talking about in terms of, they basically driving the equations, and when they were driving the equations at that particular time, they mention all those one by one everything, and they try to correlate with the bsim thing. So maybe if you will just search the Google, you can easily find out those bsim related model files and the respective book. So if you're doing a research, that's going to be very helpful for you guys. Now, this is the documentation. Let me finish this documentation part, and then we will take a small break. And then I will also just check, like, okay, what's basically your questions also. Just give me 1 second. Okay, so now from the documentation, I have just 5 slides. I will just run through these 5 slides very fast, just to give you an idea what all information is required, and what all those informations like from the foundry perspective, how they provide you. Everything is in terms of a PDF document. Remember, I'm not going to talk about anything which is in these next 5 slides, which is outside the PDF. Everything is going to be in a PDF format. So you can understand, like, okay, how this documentation is important, and if you know how to read those things, then it's very is going to help you to understand the PDK perspective also. And for each and everything, they will just mention, like, bonding pad. It addresses the rules and the guideline for the layout pad structure. So the if whenever we are talking about the a particular chip, then outside of that particular chip, outside boundary, basically we apply a certain pad. So here we are talking about the guidelines of those pad structures. Chip finishing instructions. So in terms of their die seal thing, the spatial structures, spatial layout structures, the foundry is going to provide you that particular part. When I'm talking about the design layout rules, so in terms of the DRC, LVS, geometrical rules, like I give you an idea, like, okay, if there are two shapes, what should be the size, what should be the distance, what should be the other criteria. So those are the things which that we are going to take care here. Not we, means the those are the things foundry will document here, and they will give you in a very well documented manner, in terms of the pictorial, in terms of the rules also. This is basically the design manual related thing, like they will tell you the documentation document name also. So I specifically mentioned name of the document that includes the design rules. So they will provide you a separate document where they will just mention the name of the document and version of the document. So I still remember we started when I was I think in a synopsis or maybe one of my company. Yeah, in a synopsis, if I remember correctly, I started working on a particular process. I just we have to make certain changes in the PDK, and when I started that particular part, so I was referring one document and I almost did I think 70-80%. I was like, okay, I will just finish it off. And then it's basically the reason I remember this thing. It was a Diwali break, and my manager said like, okay, you have to just implement these particular part, and then you can go for a 2 week of Diwali break. I was like, okay, it's good. I will just go with that particular thing. But just so I worked almost like I think 3 week or 4 week, and I finished almost like 70%, 80% of that. Then I received one mail, and in that particular mail, what happened? Uh, the Foundry changed couple of things, and they said, like, okay, we released a new version, and means they just released one document basically, and they said like, okay, this is the updated one. And in that document, what happened? They changed the document version. They said like, okay, the document version is different. Now you can imagine like, okay, you're working for 4 week and your document version is changed because now the new version is going to come. So now you don't know what are the changes happen in that the new version. They just said like, okay, there are a couple of layout rules. Those have changed. So now you have to wait that particular part. And I was like, okay, still I have 1 week or the 2 week. If I will receive that updated document, then maybe I can just finish it off. And you will not believe, guys, like for the entire week, I didn't receive that particular document. At last, I received it. Thank God. It's just like there was only two small changes, but those two small changes, I have to make the thing. I have to just make changes in the PDK. I did it, and I'm done. But let us suppose if I missed any of this thing. If I have missed this particular document where they have mentioned like, okay, new document is going to be released, and then that's going to create a problem. So as a part of a PDK, we have to add all these things. We have to make sure like, okay, we are working correctly, and we are just very tightly working with the Foundry, because that's very important. Device cross sections, so they will just draw the different device cross section. If you remember, I explained you like side view, top view, bottom view. They will give you all those things so that you can visualize those particular part. They will also give you the electrical parameters, like, okay, in terms of the peak current, in terms of the RMS current, in terms of your average current. So they will give you all those particular parts. So they, in a VLSI, we do a lot of EM electromigration and IR drop checks we do. So those things they will mention. Like here, you will see they have the electrical rule checking. Like, okay, how you're going to check it, what is going to be your current density, and whether that particular current density is good for your design or not. So it's not like you just create a structure and that's good enough. It's just like a Foundry is saying like, okay, in this particular structure, if the current is going to flow more than this particular amount, that means now we are talking about the current density. Now if that is going to happen, then there is a problem. Then there is a problem, like maybe it is going to heat up at that particular place. Something can just broke down. Maybe it can be like um, short circuit, or maybe it can be an open circuit. So all those things we have to take care. Now when it comes to the ESD related things, so they will tell you like, okay, what should be the structure for your uh, basically the devices which you are going to use, or the structure which you are going to make for the ESD protection related thing. They will tell you in terms of the interconnect resistance and the capacitance related thing. They will also tell you how you can avoid a latch up issues, and what are the different rules, because it's not like in a book, a latch up and they said like, okay, the guard ring is going to help you, the tap cell is going to help you for the latch up prevention, but there may be some other recommendation also. So there are different processes also. With respect to the process, your latch up rules are going to change, and those things you should understand. Now when we are working in a analog side, then all these things are very important, because anything in a digital is very easy, 0 1 0 1 0 1, and we know nothing is going to pass through the substrate. Even though we know like, okay, something can pass through the substrate, but in a digital we still we are okay. But when we are talking about the analog, when we are talking about the signals, when you are talking about the mixed signals, I will more precisely, basically, then a lot of things happen in the substrate itself. So you should know like, okay, what are those things are there. Now, there are certain GDS related thing I already mentioned. Then there are certain noise related things. So this noise model, that is very important for you guys. So when you are when you are going to design a antenna, when you are going to talk about a particular transmission lines, so how what is the reverse path? How what and you are saying, okay, it's supposed to be very accurate and the precision. And what about if there is any noise? From where that noise is coming, how you're going to model that particular noise and just simulate that particular part. So there is a basically the noise modeling is there's I would say from the analog point of view is very important. So Foundry is going to provide you all those information, like, okay, in this particular way you should do the noise modeling. Now whether that your tool is working correctly or not, that is not their problem, but at least they will tell you like, okay, this is, in this particular process the substrate has this much of noise, so to reduce this particular noise, you have to go with this particular process. So the process is going to change as per your design, I would say, or as per your requirement. So in communication devices, you know better than me. Like, okay, any communication devices, even if a small noise is there, that's going to change everything. So you have to make your circuit as a noise free. Then you have to take a very precaution at each and every stage. It should not be like, okay, the encoding, decoding, encryption, decryption, everything you did it on a software side, on a the outside, everything you are doing from the power point of view, like, okay, I will just increase the power, and then in the receiver side, I will just remove the noise, I will average all other things. But what about within the chip itself? Because of a noise, one bit is changed from 1 to 0, or your transmitted data itself is a problem, and you don't know where exactly is the problem. It's not a problem in your software point of view, it's not a problem in your encryption, it's not a problem in your data bit itself, it's a problem in the hardware. The noise is coming from the device level itself, from the hardware level itself. So you have to make sure that particular part. So all these like I have just mentioned here, it will tell you like, okay, mask related thing, the fabrication related thing, they will give you the information, they will tell you the local process variation, they will tell you the noise model, they will tell you the interface of the pixel. Obviously if they are providing you all those pieces, then they have to just write all the information in a part of a document also. They have to talk about the process control monitor related thing, they have to talk about the RF modeling. So they are going to talk about the RF parameters and their modeling issues. Like, okay, these are the modeling issues in this particular process. So that you should not just blindly just pick a particular process and you say like, okay, I'm going to design using this particular process, because Foundry has to tell like, okay, this process is not going to help you out because there are a lot of issues there. So they have to document this thing somewhere, like, okay, this is going to be this is not good for this particular frequency level, this is not good for if you are expecting this type of quality. So they will tell you that particular part. And yes, I think these are the document related information. Then from the deliverable point of view, there are two categories. One is the front end deliveries and the another is back end deliveries. When I'm talking about the front end and the back end deliveries, basically, so it's just a matter of uh, the what I'm just putting in which particular bucket. So these are the two things which comes in as a part of a front end deliveries. Rest of the portion is part of a back end deliveries. Now when I'm talking about the front end and the back end, so just to give you an idea from the semiconductor point of view, in a layman language, you can say till the time you are talking about the code, till the time you're talking about you're just away from the physical dimensions, basically. Till the time you're just talking about, let us suppose the schematic you're talking about the simulation, you're talking about the Verilog code, you're talking about everything else where the physical dimensions are not into the picture. So those things come into the front end side, because that's something you can see at the end of the day. But whenever there is a something which is a part of a physical dimensions, like anything related to the physical dimensions, so metal layers, or maybe if even if you're saying the boundary coordinates, if you're saying like, okay, within this particular area my design supposed to be there, so that comes as a part of a back-end delivery. Now, why I'm talking about the front end and the back end, the portion, because whenever we are talking about the simulation and everything, so most of the time you are going to do the simulation everything in the front end side only. So from the tool perspective, the front end tools are different, the back end tools are different, the flow of the back end tools are different, the flow of the front end tools are different. And it's my understanding, maybe any one of you can comment on that particular part, but in general, till that time you are not doing any uh, fabrication related stuff, you don't want to fabricate anything, till that time you don't need any backend related flow, backend related tools. So you need only a front end related thing. So till the time you are doing experiment in terms of simulation, and you are just trying to understand like, okay, what is going to be the output, the power, the in terms of the maybe the timing, the waveforms we are talking about, the characteristics we are talking about. So all those things comes in the front end side. So in a communication, let us suppose you are doing certain simulation using the MATLAB or maybe some simulation tool, you are using that particular part. So those comes as a part of a front end thing. And nowadays we are lucky, like in a front end side, you will see a lot of free tools, lot of open source tools, or even the front end tools from the simulation point of view. Those tools or those flows are easily available in a very lesser price. So even like, okay, as a I can tell in a different way. As an individual, I'm talking about, I'm not talking about from the university or the college. As an individual, people can afford buying those simulation tools. That's a good part of the front end side. In a back end side, as an individual, you cannot buy until unless you're talking about in terms of open source tools. And that's the reason in a back end, the open source tools play a very important role nowadays, because people are facing a lot of problem there. So in a PDK also, maybe you don't need to have a complete PDK. So maybe you can have a the PDK for the front end deliverables. So that's the reason I just divided this particular part, just to give an idea. So if I'm talking about the PDK, the six division, if I'm talking about, so no need of those six things, six category, everything you don't need at a very first day. You can start everything with the front end deliverables, where we are talking about the symbols, where we are talking about the spice simulation, we are talking about in that particular way. So in a schematic, in a tools, if you have all those libraries, or the I would say the front end PDK, you can create your circuit, simulate your circuit, see what is the output, the waveform, everything you can easily see that particular part. But when we are talking about the very specific VLSI specific fabrication specific thing, then you need a backend delivery, backend portion. So like it's my understanding most of you here are going to do a lot of simulation related things. So if that is the case, and you're more oriented toward the communication side, then the simulation is more than enough for you guys. That means from the PDK point of view, the front end PDK is if you have the front end PDK, you can work on that particular part. And for that, you can go with the free one also. And like I said, it's affordable. You can just go in the market, just to check the website. There are a couple of companies, they will give you the tool also, and they will give you the PDK, the respective PDK also. That is a front end PDK. They can give you everything, and you can buy and you can just do the simulation and everything, and you can just do the rest of the experiment. You can do very easily. So I'm not going to discuss here in terms of the front end. I would say the flow and the tool flow, because as such it is a standard one, but I'm not going to discuss that particular part. You can easily search the website, and maybe you can just check the Selvico website. You can just see, and there is a one more key site. I think you can just note down those things, and you can just check. You can get a lot of documentation, or if you just search in a Google, like, okay, front end PDK for RF communication or the 5G, you will get a lot of data. And I was just checking yesterday. I think in couple of places you can they allow you to download also. And when I was just checking, that's basically the free of cost. And in some places the amount itself is very less. When I'm saying this very less, is just maybe like a couple of hundreds dollar, I would say. In some place, like, okay, it is. As per my understanding, if even if you are purchasing any tool within a range of a 1 lakh rupees in an Indian currency, if I will talk about, that is affordable by an individual person. Because in a backend side, even if you will go with the single license of a Cadence backend tool, is going to be like 1 CR. If the commercial license, if you want to purchase it, I'm not talking about the educational license. So it's a commercial license. So now you can understand 1 CR and the 1 lakh. It's a pretty much a lot of differences are there. Okay, so I will just take a couple of more minutes before we will go for the break, because Ashish shared with me, like, okay, at the 12 o'clock mostly we usually take a break. Then now there are a couple of things in the PDK related things. This is the something which definitely all of you are going to ask. Why to use PDK? Why can't we design everything our own requirement? These are the things I think you guys were asking. Why can't we design in terms of uh, as per the ourselves, as per the foundry requirement? What if we will design it? If someone will design, why can't we design it? Cadence is doing, why can't I do it? I can also do it. Why should I pay huge amount to the Cadence or the Synopsys or maybe the any particular foundry? Because obviously that's my money. If and I'm a student, why should I do that particular part? Why should we dependent on someone else? Obviously, that's the first question everyone is going to ask. And is it necessary to use a PDK? So I think couple of questions I already answered. Why to use PDK? But there are a couple of things still. Maybe you're thinking like, okay, you need that particular part. So first of all, why PDK? So there are four different things. Design productivity. When I'm talking about the design productivity, so if I will ask you, like, okay, just design a, low pass filter. So when I'm talking about the low pass filter designing, so first of all, if you have to do everything from the scratch, you are going to design the capacitor also, resistor also. But if I will give you the symbols, if I will give you the characterize the everything, what you are going to do? We will just drag and drop, create a circuit, connect the wires, voltage source, and you just simulate and you say like, okay, this is a low pass filter, this is the output waveform. So that means from the you can start like this. Just I think in a similar fashion, Ashish explained you like, okay, what exactly you can do, how can you play with the tools, design quality. So everyone is on the same plate. Everyone is using the same same basically the models, I would say. So the quality is going to be the good one, and those things are already verified, I would say. That's the reason I says pre-qualified, pre-configured things are there. So it's not like if tomorrow Ashish is going to check, okay, let me first check whether this is meeting all the requirement or not. So that's a something. So you can design yourself. I'm not saying you cannot design. You can do that particular part, but then Ashish has to check the everything. Yeah, time to market. If Ashish want to uh, do something, and if this particular best example is this particular workshop, and in this particular workshop, if we want you to design a small low pass filter and just if we want you to just simulate it and just see what is the output and waveform, how you're going to make changes in the input and you will get the output, you can do it within a 2 week. But if we have to ask you just to design a capacitor, so we have to solve a lot of your problems. So that's not basically a time to market related thing. Profitability. This is a something is very tricky thing. I would say the last thing you can, okay, for the companies it is a profitable, and but it's not profitable for me. But if you're talking about uh, from the production point of view, so let us suppose today you are you're designing a low pass filter. Tomorrow we change certain specifications of the low pass filter. Then you have to again someone else will come, they say like, okay, now we want to design the low pass filter for this particular range. Now then you're not supposed to rework everything from the scratch. You're not supposed to design everything. If it's available in the PDK, you can just use it. Once you know very well, like, okay, this is the way I'm going to design a low pass filter, then it's just like you're going to just change the maybe the specification of capacitor, resistor, and you can say like, okay, done. I'm good. So that means your rework is the iterations I'm just talking about, that is less. So when I'm talking about the profitability, I'm just talking about from that particular perspective. Yes, if you're doing from your experiment purpose and you're saying like, okay, I have enough time, but I don't have any money, then obviously this is going to be a question like, okay, how it going to help me? But yes, if usually people usually talk from the design from the production point of view. Okay, so I think this is something we will finish after break, but before that, let me check if you guys have any question, and or you can ask questions also. It should be like Ashish should not say this thing like, okay, people are not asking any question, because he will say like, okay, so if you're not asking any questions, it means there are two things. One thing is you're not able to understand anything. The second thing is you understood everything. So the second thing is very difficult if you're not from this particular field. And if the first thing is there, you're not able to understand anything, that is not good for me. So at least just ask a couple of questions, maybe 10 questions you can ask. At least I can show to Ashish like, okay, see, people are asking questions, they are attentive. Let me start with this. Like someone asked long back. Why do we need to do the testing across the different corners? Why we can't know in advance our process corners? So you have to understand what is the meaning of the process corner. So, for example, uh, your mobile phone, and if I will tell you like, okay, this mobile phone is going to work in a 30 degrees Celsius. That means whenever the outside temperature is at 30 degrees Celsius, this phone is going to work. Then you will say like, okay, I don't need it because in India, the temperature varies within a 10 degrees Celsius at a particular state. So at a particular time, that means the day temperature and the night temperature, the maximum variation, let us suppose at 10 degrees Celsius. Then you will say like, oh, no, it's not going to work for me. I am not going to purchase it. Then I will say like, okay, I did it. So now this mobile phone is going to work between 25 degrees Celsius to the 45 degrees Celsius, or like, let us suppose the 50 degrees Celsius. That means before 25, I don't have any guarantee. After 45 or 50, I don't have any guarantee. Then again, you are not going to purchase. You will say like, what about if I will just travel to the Shimla, or what about if I will travel to the Kashmir? And let us suppose in the night, if it is a 0 degree Celsius and I stuck somewhere, then how can I make a call? So you're not going to purchase that particular part. Then what is going to happen? I will say like, okay, from 0 to, let us suppose 0 to 50 degrees Celsius. Then you will say like, okay, no. What about in a summer in a North India? And if there is a outside temperature itself is a 48, and I'm just charging my mobile phone, and when I'm just charging my mobile phone, the temperature of my mobile phone that increases, because usually that happen because it's emit a lot of heat also. And let us suppose the temperature become 55 or the 60 degrees Celsius. Then what does it mean? It's not going to work out. No, I will say like, okay, I will just give it till the 60 degrees Celsius. What about in a Kashmir in a winter season where it's going like now minus 10 degrees Celsius, and then you have a metal cover, and in that particular metal cover is again going to be like another 5 degrees Celsius, minus 15 degrees Celsius. So basically, this temperature variation is which I'm just talking about. So it's like the minus 15 to 70 degrees Celsius I'm just talking about. And this is the outside temperature. Inside, maybe it can be a little low and a little high also. So this everything you have to make sure like, okay, your single mobile phone is going to work within this particular range. And this I'm just talking about from the temperature. Similarly, the things happen with the in terms of the voltages also, in terms of the other the process, in terms of the foundry process point of view, fabrication process. So foundry itself don't know whether it is going to be your variation is in the negative or the positive. They will say like, okay, the 2 nanometer which you're talking about, the dimensions can be in a plus and minus 10%, because they don't know how things are going to change in a fabrication, because that has a dependency over the light, that has a dependency over the wavefront, that has a dependency over basically the wavelength, refraction, diffraction, all those things. So as a communication engineer, you know very well, if I will say like, okay, I need a signal at this particular place 24 cross 7, then you can say like, okay, I am going to add a one particular booster here, then only you will get it. And even in that case, if I will say this should be the intensity of my signal, it should not be more than this and less than this, you cannot give me the guarantee. The same thing happen in the fabrication side also. So I think now you have an answer like, okay, why we have to test across the different corners, and why we don't know in advance. If we know in advance, but we know in advance as a range of my design corners, range of my different the combinations, and that combination is basically we are talking about the corners. Manish was asking, actually, I read about the right Varila TCAD. Okay, so this TCAD related thing, Manish, maybe we can discuss later. Yes. And then we are talking about, once again, I'm asking what is the difference of the PDK model and open source model, such as the BSIM model, as you are showing right now. I think, Wasim, I have answered. So what you can do, you can just check the live sessions later on the YouTube, and then you will get the answer. What is the difference in the PMOS and the NMOS level? Good question. So it's a pure semiconductor related thing. Just in a couple of seconds. PMOS, NMOS. That means the P type and the N type. There we are talking about two charge carriers, the electrons and the holes. So when we are talking about the current flow, so in one, that means that in NMOS, the current flow happen using the electrons. In the PMOS, the current flow happen with the holes. And now, what how the holes generate? What is the electron? I think everyone know, like, okay, what is the electrons? But when we are talking about the holes, then you have to just go back and just see in the crystal there is a something known as the covalent bond. And if covalent bond in the sense, it's just like in a bonding in the sharing. So you share one book, I will share one book. That means now we have a equal sharing. But if you will share, I will not share, that means there is a deficiency of a one book. So that similarly in the covalent bond happen. You share one electron, I will share one electrons. I'm just talking about the two atoms. Both the atoms are going to share one electrons. Then I will say, like, okay, the covalent bonding is there. If anyone is going to share one electron, other is not going to share it, then there is a deficiency of electrons, and that is known as the holes. So that is a PMOS. So that is every this PMOS every and related thing is basically depends on your the crystal on your molecule, basically, I would say. Like, okay, how the structure is there, how the PMOS is, how the where exactly is the deficiency, and the deficiency is there, then it's become a hole. If there is extra electrons, then it become NMOS. So that is the NMOS PMOS level related thing. Now, if the current is going to flow through electrons or the holes, then definitely all the characteristics, everything is going to change, because they have a different current, they have the different capability, I would say, the parameters. So drift current and all those things come into the picture. So I think that is that's going to be too much in a semiconductor side, but you can just search on a Google PMOS, NMOS. I gave you the little bit idea. Wasim was asking, may we use the Foundry PDK in any open source EDA tools? I already gave you the answer, Wasim. Like, you can use it if your open source tool as can read those files. Then you can do that particular part. Can we apply FinFET in RF? It's a good question, and I think Ashish is the right person who can answer this particular part. FinFET in RF. So, as per my understanding, right now, from the maturity point of view, still FinFET is not good from the RF point of view. But yes, Ashish and if Aditya is there, maybe they can comment on that particular part. Now, yeah.
Yes, you can, but depends on what the application you want, right? You can we put enough power into them, or from LNA perspective, do they meet the requirements? So obviously, from design purpose, you can. The only limitation on the FinFET is that your length gets fixed. So you cannot have arbitrary length devices. So that limits your the lambda basically in your for your analog design perspective. But obviously you can, but depends whether or not we need it. Your voltages are different, and right now market wise there is not particular need, but maybe in future.
Okay. Thank you, Aditya. Yeah. See, I was saying there's more expert people here. Okay. So then. There is something open source for backend, front end. What are the various open source? I think Inderjeet, I'm not the right person. Google is the right person. So if you can just search in the Google, maybe Google can tell you everything. Like, okay, what are the different open source tool for the backend and the front end? Yeah, so you can ask Google. Google can answer you the right thing. There's one more question. The front and back end, as you have discussed, the custom semiconductor RSA design is different. So custom semiconductor category is different. Front end and back end is different. Front end and back end, I just gave you an idea in the layman language. If the physical structures are there, back end. Physical structure is not there, front end. The custom and custom in the sense, I would say the standard cell, or maybe already someone just designed that particular part, is basically someone. So it's just like um, in a from the building point of view, I'm just talking about. If in a structure everything is predefined, so not the building. I think that's not going to be the good example. The good example is going to be like in our household. Now we are talking about this furniture. So there are three type of furniture. You can just ask the carpenter. They will come. They will just come up with the raw material and they will just create everything. That is basically the custom one. Nowadays there is another one where they will just give you the predefined structures. So using those predefined structures, you can just uh, combine and you can say like, okay, my things are done. So they will say like, okay, you can come up with a you can say like, okay, it's going to be the 3-seater 5-seater sofa is going to be there. That means you can customize it, but up to a certain limit. That is a semi custom. And then the third one is like you cannot customize anything. You just go in a shop, it's a three, either 3 or 5. So both have the different things. So that's a third category. So similarly in a VLSI also, if the everything from the scratch you are defining, you are designing. So that's basically the 100% custom we are talking about. Now, if something is there and you are using that particular part, rest of the thing you are designing, that becomes the semi-custom. And there is the third one where everything is already designed by someone. You're just placing it and you're just connecting with the wires. So that's the third portion. And it every three one, it has their own pros and cons in terms of like advantage and the disadvantage. And I think you can understand with the analogy which I gave you. Okay, and there is one last one. Does PDK also take into account issue related to the high frequency of? Yes, so I gave in this thing, the RF related PDK is there. What mostly use PDK tools, the most popular tools? Most popular tools in the PDK. Every tool should have a PDK. So I think if you are asking that particular part, open source to you mention why India don't have semiconductor foundry. Say, come on, guys. So it's like SCL is there. So don't say like, okay, you don't have semiconductor foundries. SCL is the best example we have. But yeah, so there are a lot of other things. And so you cannot say like, okay, we don't have the foundries in the lower technology node. So there are a lot of other challenges are there. This is not the right forum, I would say, just to answer this particular question. Whether the founders come forward to give the PDK details if we wish to come up with a joint venture if a project is assigned to MTech student. Yes, so you are right. It can be done. And so if your university, they have a tie-up with the foundries and you can work as a joint venture also. So best example, maybe you can just talk to the SCL Chandigarh. So with them, you can work on that particular part. And if you have a good understanding about the tool and the process, you can do that particular thing. Okay. Okay. If anyone have any other question, you can ask. Else, I'm already 12 minutes, 13 minutes, I think. Over. Ashish, the time slot for the break is 12 to 12:15. Am I right?
Yes, sir.
Yes.
So that
So no problem. We can now break like for 12:15 to 12:30. We'll take break. Then we will continue from 12:30.
Yeah, we can do that particular part. Miss, if you want to stay here, I'm okay. I can discuss. I don't need any break. But
thank you,
yes,
sir.
okay.
Can I make one announcement?
Yes, yes, it's your forum. It's your basically everything is yours.
Thank you, sir. Dear participant, the YouTube channel is not for marking any official attendance. The attendance will be generated by the Cisco WebEx and we will be considering that attendance only. We notify the same from the first day. Please don't consider that if you are attending the session on YouTube and you are dropping your details in the YouTube chat, it will not be considered. The same thing has also been notified to you through the instructions and over the platform also repeatedly we have announced the same. So please join us through the event link, not by the YouTube channel. That is only for your reference. For study purpose, the recorded lectures are available. Thank you.
Thank you, ma'am. And YouTube channel is basically for those who don't need a certificate also. Okay, and they missed it. They missed
Yes.
just to register on time.
Yes. Yeah. Thank you.
Great. So I think someone have one question. Let me answer that particular part, and the other people can take a break also. And maybe in between, I will just go for 1 minute. Yeah. Okay. So I don't have water right now. Yeah. So how will we know? Okay. So one question is which nanometer is good for the future communication? Okay. And Ram Babu. So Ram Babu, can you just let me know which nanometer was good for the past communication and which nanometer is good for the present communication? I think then I can answer your question also, which is a good one for your future communication. Babu, anything? So the reason I'm asking, like, okay, which nanometer is good for the future communication? So what do you know the future? So in a future, if you're talking about the 5G, then definitely that's the reason that's we are going to discuss. Yeah. So we will discuss that particular part, like okay, the nanometer which you're talking about, and we will discuss little bit. But again, it depends. Like okay, what are the challenges are there? On the basis of that challenges, how you're going to change your process and all those things. So next question is how will we know about what frequency, especially in the millimeter wave design, the parasitic extraction model from a particular EDA tool will be insufficient and we need to use a EM solver for complete parasitic extraction like areas. So if when you're talking about the EM solver, are you talking about the field solver basically? Am I right? Or what is that EM solver? If somehow I become confused. Yeah, so field solver. So okay, so if I understood your question, the question is very good. Now you're talking about from the extraction point of view, you're saying till what frequency the parasitic extraction model for a particular EDA tool is sufficient. Now the question, so there are a couple of things which I think when you have mentioned when you are just uh, uh, frame this question, so you already have answered that particular part. One thing is you have mentioned particular EDA tool will be insufficient. So if that means a particular EDA tool is going to support a particular extraction model. Now it is a responsibility of a EDA tool whether they are going to support the extraction model or not. The pattern basically the pattern which you are asking about. So now what happened as a EDA vendor if I am supporting a particular um, process, then I'm going to redesign my patterns. So if you're thinking like, okay, I created one pattern today, and that pattern is going to work for the entire generation, that's not the thing. The patterns which I'm going to generate today those patterns are going to change as a technology nodes are going to change. So uh, in a semiconductor industry, there are a couple of things which we usually use. One thing is a design specific data. Another thing is a technology specific data. The third one is a process specific data. So when I'm talking about the design specific data, that means within a particular process, in a particular technology node, if we have a different kind of design, like digital design, analog design, low power design, in a particular technology node I'm just talking about, then is going to be a different one. So that's the reason we usually foundry usually tell you like, okay, in this particular technology with this particular process, you can come up with these type of designs. You can only do these type of designing, you can do it. So when it comes to the extraction side, so I will just jump directly to your question. So when we are talking about the extraction models, basically, which I was just talking about in terms of the predefined structures, the patterns, it is a technology specific. So if you're going to change the technology, the patterns are going to change because the dimensions are going to change, their rules are going to change, their the way the capacitance you're going to calculate, the complexity, the variation, everything is going to change. So if you are, let us suppose if you're in a 180 nanometer, if you're if I'm talking about a particular process, so in that particular process, if I have a particular structure, so it's going to work out there. That's not a problem. Now, when I'm talking about the modeling of the capacitance, and when I'm talking about like, okay, what are the other side effects? So you can say like, okay, my capacitor, the signal is going to flow like 0101. What is going to be the capacitor related thing? For analog, is it going to change? Maybe in analog, something else will come into the picture, and that's something else which I'm just talking about, like in a capacitor, like, okay, in a if you're talking about the frequency, then there's some omega will be there. All those capacitance has a dependency over that particular part. So obviously, if you need a capacitor information, then I will add that particular parameter in my calculation, and I will tell you like, okay, this is the what is that the lookup table. This particular pattern has this particular cap, and these are the parameters. So we can calculate in that particular way. I think I answer your question, Soham. I'm not sure, like, okay, if that was your complete question. Someone was asking how many layers in the mobile phone IC. Okay. And similarly, okay, so Vijay was asking how many layers in the design mobile phone IC and why different layers are needed. So let me ask you the last question first, the answer of the last one. Why different layers are needed? The answer is why you need the bridges in the road, why you need uh, underpath, why you need multi-level bridges on the road. Basically, what is happening, you want to reach from one point to the another point, one destination. You will say like, okay, you want to travel to one point to the another point, and shortest path. If I will tell you, I don't know like where exactly you're staying, like, but let us suppose if you are in a Delhi somewhere, and if I will tell you like, okay, you have to just cross Yamuna. So just a best example. Now, if I will say like, okay, for that to cross the Yamuna, you have to just travel another 20 kilometer. Then there is a bridge. You just cross it, and then you have to come back. Then you will say like, okay, what is this? 20 kilometer and 20 kilometer, 40 kilometer I have to travel just to reach the other side of the river. In place of that, why can't we just come up with a one bridge here? So that bridge, what is that particular bridge? That is basically we're talking about the uh, maybe one more level of battle. Then Similarly, maybe you can say like, okay, now we have this red light thing. The crossing is there. If you want to make it as a red light free, then definitely red light free. That means anyone can travel anywhere. So just think, in a red light, if you want to make it 100% red light free, then how many levels of roads you have to come up? Anyone can turn in any direction, maybe in the left also, right also, in the straight also, from everywhere. Then definitely there are going to be the multiple levels of roads are going to be there. So similarly in our circuit also, see, there is a spray scrunch. If signal supposed to travel one place to the another place, and you cannot do everything in a single layer. You have to go with the multiple layers. So the concept of the multiple layers depends on the complexity of your design. If you don't have any complex design, if it is just a two inverters, you're just connecting with those two inverters, I just need a one layer. That metal one can help me out. Now, if we are talking about in a small area, if there are 100 of inverters are there and you want to just connect those particular part, then definitely you have to jump to second level or the third level. So that's the reason, like, okay, why different layers are needed. Now the next question is, how many layers in the mobile phone IC? So you have to tell me what is how many transistors are there in your mobile IC. What is the complexity of your mobile IC? So if you will tell me the transistor count, if you will just tell me the complexity of your mobile IC, I can tell you, like, okay, maybe it is say 8 layers, 12 layers, maybe it's 15 layers, maybe it's 6 layers only. Depending upon the complexity of the design IC, the number of layers are going to increase. So if you will ask me, I don't know. There are couple of there are designs which are 6 metal stack. So we usually talk about the metal stack. 6 metal stack also, 10 metal stack also, 15 metal stack also. So those things are there, the mobile IC also. As is it clear? Did I answer your question? I hope so. Okay. Anyone else have any other question? So very less question. So Aditya was saying like, okay, very few people are asking question. So I'm sure like, okay, later he will definitely tell me like, okay, see, no one understood your your talk. Okay, guys, just give me. I'm just unsharing my window. Let me see like, okay, how much. How much data? Okay, so I was thinking like, okay, it will take a lot of. I will finish little early, but looks like I have to skip couple of slides. Okay. Okay, great. Firoza ma'am, can we start now? It's 12:31.
Yes, sir, we can start, sir. The participants are already connected, sir.
Yeah, great. So, guys, everyone, like, any one of you have anything before we start?
The last input was like Soham sir, he dropped in the chat box like, sir, thank you. It was a good presentation.
Thank you. Thanks a lot.
Okay, thank you, sir.
Okay, thank you. Okay, so I think we can start now. There is a one question it's asking by Vijay, what way layer differentiate frequency, power, or current? What way layer differentiate frequency, power, or current? Okay, so think from so I will answer this thing in a different way. What is a layer? Basically, it's a metal layer. So when I'm talking about the metal layer, so metal layer can have a or any particular layer like in a device or anything. It can have resistance. It can have capacitance, obviously with respect to the with the other layers, and it can have the third component as an inductor. Now, when you're talking about the frequency, power, and the current, I'm 100% sure you know better than me the relationship of these three components with the frequency. Like, okay, how the frequency is going to change if you're going to change any of these three component or in the different way also. But I'm just talking because your question is with respect to the frequency, power, and current, how the frequency is going to change if you're going to change any of these three components, and similarly the power and the current. And when I'm talking about the layers, when I'm talking about the metals, then I'm just talking about the metal 1, metal 2, metal 3. Then every metal has its own characteristics. It has on properties. Like, okay, this is going to be the minimum weight. This is going to be the thickness. This is going to be the uh, other parameters. We will discuss one of the packaging technique, not the packaging technique, it's like one of the challenge we will discuss in some time, where I will just show you one or two configurations of the different things. So basically, what happen if you will make any changes there? Obviously, indirectly, you're making some changes in somewhere else. So in a communication, if I'm saying it's a short wire, then you know, if it is a short wire, which particular parameter is going to change and how it is going to affect your power, frequency, and the current. So I'm not an expert in that particular field where I can just give you the right answer, right answer in the sense the direct relationship, like, okay, this is directly related to this particular part in this with this equations, because I always say I'm not an equation guy. So I don't remember things with the equations, but yes, from the concept point of view, this is the concept. Now, rest of the portion you can check, like, okay, how uh, things are going to be different, or maybe you can ask this question to Aditya or Ashish. They can comment on that particular part. Okay, let's move and let me just finish it as soon as possible. I don't want to take your whole day because I have a lot of slides right now. So let's finish within the next, I think, 5 minutes, the process design quality check. So now the question is how we will talk about from the quality check point of view. So if there is a PDK, so when I'm talking about the quality check, I'm just talking about from two perspective. You have designed a PDK or you have received a PDK. So if you have received a PDK from someone, maybe it's a TSMC and the Cadence, and you as a engineer in a Qualcomm, or maybe some company which is working on a some 5G related project. So the question come, are you going to blindly believe, like, okay, whatever these two people are saying, the foundry and the Cadence, this is good? Because if you will believe and something happened tomorrow, let us suppose something happened tomorrow, even if they are ready to pay you some amount, but there is a possibility that in a somewhere in a fine print they will say, like, okay, it's a like like in a insurance or in a loan or somewhere, it's always written like, okay, we can change the policy without any prior notice. Maybe somewhere it is written in that particular way, like, okay, you have to, just 1 second, guys. So maybe somewhere it is written like, okay, you have to follow our recommended rules, and maybe you just miss that particular part, and tomorrow they will say, like, okay, see, we have mentioned this is the recommendation way, so why can't you just follow that particular part? So you should know what is the quality of the PDK, and for that particular thing, what are the different checks. We will just say, like, okay, how foundries are going to provide you the quality checks, and just the tables. So I will just show you a couple of tables. So when it comes to the quality point of view, it is the accuracy and the clarity from that timing domain point of view, from the characterization point of view, from the RF model point of view. Someone was asking about the RF PDK. Yes, there is a RF PDK, and like in terms of the noise, in terms of different type of noise, like high frequency noise, low frequency noise. Then we are talking about the passive circuits, whether those are accurate or not. So that you have to make sure, double check, I would say. You have to make sure, like, okay, things are good. Then it is integrate, whether you can integrate those things, whatever the PDK they have provided, if there are any pieces with whether those you can integrate properly or not. So see, it's a human error. Anything can happen. Maybe Foundry point of view also, something can happen. Maybe it is the EDA point of view, something can happen. Tomorrow, if something just messed up and they will say like, okay, we will give you the, for the next 2 year, we will give you the entire tool cost as a free of cost. So what exactly you're going to do? You have wasted your 1 year, the manpower, fabrication. You have wasted so much of money in the fabrication thing. And if you are not chip is not working, maybe they will say like, okay, we will just give you the return of your fabrication cost. But from the time to market point of view, obviously, you maybe lose something from your competitor and all those things. So that means you have to do double check, and that particular part is very important. So from that point of view, if I will just talk like, okay, how you're going to build a good PDK, or if I will just talk about how you're going to make sure like, okay, things are good. So you should know what is the specification. You should be able to understand the foundry documentation, then create a front end kit, back end kit, verify those kit, package those kit, and then support that particular part. So someone was asking in the chat like, okay, how I can create a PDK? Can I write a PDK? Yes, you can do it. And these are the steps. And I was from the like in the last 2.5 hours, I'm just telling again and again. It is basically related to the foundry. It's related to the tools. So, and that's the reason this is the process. The second thing itself is mentioned like, okay, collect the foundry document, because only on the basis of that you can create the PDK. Front end, back end, and verification is very important. And then package it the way you want to package it. Package in the sense, I'm not just talking about just the box and or something. It's just like in a directory structure. Like, okay, this is a spice file in a particular directory. You just keep it everything. This is a technology file. Like I came up with the 6 different category. You can just come up with that particular part. Checklist. So these are a couple of checklists. Here you can see all the documentation point of view. What are the documentation number, the section, revision dates? So we do in that particular way. So whenever someone is going to create a PDK check, so they have to do in this particular fashion. Like, okay, what is the documentation title and all those things? Because this is a something which is where the human is working. You and me are working. And if we don't have any and this is something which we will pass between the people. So documentation is very important, and there are a lot of people in the PDK. They work on this particular part. This is very important. It's not like any clerical work. Okay, anyone can do it. No, anyone cannot do this particular part. See, tool support. What are the different tool supports you are doing? Which version of the tool we are talking about? When that particular version is released? So you can see like, okay, I just captured couple of tools are there. Like, okay, if and you can just divide it like in terms of the back end and the front end related thing. So here you can write the tool type, then you can just write the name and the vendor, but which particular what is the checklist basically. So whenever you're going to talk to any particular person, and you will say like, okay, can you just provide me the PDK? You can just ask like, okay, what is the checklist? You know this particular part now. Like, okay, for which particular vendor, which particular tool your PDK is working. So you will get with the PDK, you will get in somewhere it is written in some README file like, okay, these tools we are supporting, these technology nodes we are supporting, this is the version of a particular tool we are supporting. Just if they are providing you certain pieces, they are providing you certain device related things. So how they are going to provide you, just to give you an idea, this is the device I'm talking about. I was talking about MOS, BJT, diode, capacitor, resistor, inductor, vectors. So all these things are there. How they are going to provide you, like, okay, we are talking about the NMOS, PMOS, low voltage, high voltage, maybe LVT, HVT. We are talking about the thick oxide, floating gates. So these are the different types. So it's not like an NMOS is a one NMOS is one NMOS. There are the different type of NMOS also there. Similarly, in the BJT side, in the diode side, the capacitor, what type of capacitor you're talking about? You're talking about poly to poly, or you're talking about the MEM, or you're talking about the tunnel. So all different type of capacitors are there. So all these things will be there, and they will just mention very clearly, like, okay, these are These are basically my devices. And now if devices are there, then how you have performed the test, what are the tests you have performed. So you can just write what the device type, what is the device name, what is the model name. If you have any comments, you can just say like, okay, how many terminals are there, whether the symbol is available in my library, in my in my PDK or not, what is basically the simulation netlist is there, whether the LVS netlist is there, whether we have the testing, whether you have done the testing, all these particular part. So you will see in a documentation, you will see in the PDK all these details, and they will give you, they have to give you. And if they will not give you, let us suppose something is missing, then you have to make sure, look, okay, your PDK is a good one or not. So this is just a snapshot of a couple of checks, but in reality this table is going to increase. Like, okay, there are maybe like 4 5 another columns will be there. Okay, so that's all from the PDK point of view. I took a lot of time just to explain you the PDK, but I think that's very important if you want to understand like the integration between the PDK in terms of the communication field and the semiconductor field. Now, this packaging, I will just give you an idea. This is more or less related to the technology, the advanced research and all those things. I will, like I said, I will not discuss too much in detail, because each and everything, a lot of people are doing a lot of research. You guys are MTech or the PhD scholars, so you can just go back, check the IEEE papers. Even I have captured a couple of things from the website. So what first you have to understand from the packaging point of view, like from when I'm talking about the 5G, then what can be the challenges. Now from the 5G things, if I will just mark couple of important thing, it is basically the high speed, high transmission capacity, and the low latency we are talking about. Now that's a goal we are talking about. So if that is a thing, then in a semiconductor, if I will say like, okay, we will go with the bulky devices, no. So we cannot go with the bulky devices. So I have a separate slide for the 5G challenges in a millimeter waves. So what happened? What are the challenges there? But the thing is, it's not like uh, the millimeter waves. If we are talking about, we are going to use the first time. There was a time in the past also we have used it, but for those particular device, for those particular thing, it was we are okay to use a bulky devices. But now we are just talking about from the communication, the 5G, the mobile related thing we are talking about. That means everything is going to be like a scaling point of view. So there are two things. One thing is the scaling, another thing is packaging. How you're going to do the package. Basically, we just want to reduce the dimensions and all those things. So if we are talking about the technology scaling, like we're talking about the nanometer and all those things, then basically there are a lot of checks and all those things. I will discuss those things later on little bit. But the important thing is the packaging point of view. Can we reduce the dimensions of my product by using this some different type of packaging? So you have to understand like, okay, uh, you have to focus on these three things: high speed, high transmission capacity, and the low latency. And with that, again, obviously the power consumption, you want to go with the low. Heat dissipation, that should be low. So everything's supposed to be on the lower side. The product dimension is also supposed to be on the lower side. So can we tackle these issues with the help of some packaging things? So this advanced packaging come into the picture. Now when I'm talking about the advanced packaging, so then I'm just dividing this advanced packaging into the two type of devices. One is terminal devices, where your smartphones and the notebook come into the picture. And then the second thing is basically the cloud devices, where we are talking about the servers, we are talking about the base stations. So all those things come into the picture. Now here, my focus is going to be again this particular part. obviously the cloud, these things, the servers and all, I'm not going to discuss right now. I will just give you the little bit idea about this particular part, the application process, and I will just talk about a little bit about the antenna thing. So this is the application process. So it's basically the connection methods, how you are going to connect the inside, whatever be your I would say in the layman language, I would say in the chip, inside the chip, you have AND gate, NAND gate, resistor, capacitor, and all those things. How you're going to connect, how you're going to come up with some method which is basically going to communicate with the outside world. That is very important. So that's the something we are just talking about. Like, okay, conventionally we were talking about the wire bonding. There was a uh, there are a lot of things that there are a lot of I would say research happened in the past also. Even a lot of people are working on this particular side. I just gave you one three things, like, okay, how you can reduce the size also, and in terms of like how things happen, like, okay, if you are talking about the wire bond, this is basically the we usually talk about the substrate, we usually talk about the die, we usually talk about how these things are connected with the die. Sorry. Now in a flip chip, something uh, these things happen, like uh, you can have maybe, so you can understand these two figure very clearly. Just to give you an idea, connections are here in the top. Here you can see. So if any one of you have any idea about the semiconductor, what happened, like, okay, there is a metal 1, metal 2, metal 3, metal 4, and then topmost is going to be your the layer, and through the topmost, so if it is your top one, so the connections are like this. The outside you will get the connections, and then you are going to connect it like this particular part. So what is this flip chip? As a name, say flip chip. That means you just flip this particular die, because all the connections are here at the top. All the 1, 2, 3, 4, 5, 6, everything is here. So what you can do, you can just flip it, and then you can use all these things, and you can just connect with this particular part. That's again one of the way. There is a WLP process. We will discuss about the WLP process. So this is something help us a lot nowadays when we are talking about the future. Someone is asking about future communication. Yeah, so that's the something is this thing. When we are talking about the antenna, so in an antenna, what in case of an antenna, basically the important thing is the antenna dimensions. You know the path losses, you know the signal accuracy. So these are the terminology which is always uh, I would say the moment anyone is going to ask you about the antenna, then you will say, okay, these are the things. What is so the even the dimensions of the antenna, that the power basically related things. So all those things uh, suddenly comes into your mind, like, okay, these are the things. And then we usually talk about, like, okay, antenna volume is determined by the frequency in a millimeter wave. If I'm talking about the antenna dimensions, ranges are going to change. Similarly, in terms of the accuracy point of view also, like, okay, the when we are talking about the signal ins and outs, so transmission side from the data accuracy point of view, so those are the things which we have to take care. When it comes to the power loss, we are just talking about, like, okay, in a high frequency waves, uh, what happened. So then the terminology come into the picture, the penetration related thing, the attenuation related things come into the picture, and those losses, what are those things which is going to play a very important role uh, when we are going to design basically the antenna. So there are a couple of I would say the packaging related, antenna related things. So like I said, I'm just giving you an idea. Like, okay, there are different researches are going on even in the antenna side also. So there are something like the RF chip, if we are talking about in the substrate or if it is outside the substrate, we can talk about that particular part. So it's a big subject. But yes, when we are talking about the packaging, so uh, these things are very important. Whether you want to fabricate the antenna within the chip or whether you want to fabricate the antenna outside the chip, how you're going to connect it, even if it is a single wire, and if the length of the wire is uh, more than a particular value, so you can say like, okay, if the length is more, then it's going to catch the signal. Very good signal will be there. But that depends like, okay, which frequency we are talking about, and how we are going to design it, what are the side effects of that particular portion. So it's basically outside the thing. Similarly, inside the chip also, inter-die communication is going to happen. Like, okay, there are different antenna related rules are there. There are different how can I explain you, like, okay, the communication happen within the chip. So if I'm talking about a particular wire, it is going to emit a signal outside in a free environment. But if that wire is inside the chip, that inside the chip also it can work as a antenna also. So all those things we have to take care when we are talking about the from the packaging point of view. Maybe if you will just search it, then you will find a lot of articles in those directions, like, okay, how we decide basically the line and the spacing, and how we when we are talking about the pins, when we are talking about the performance, how we design that particular part. Now again, same thing which I have just discussed in terms of the 5G. Now we are talking about here. I just giving you the one picture of the band related thing. I remember in one of the talk, Ashish represented this particular part in a very far better way. But I just capture this particular picture just to remind you once again, like, okay, what frequency band we are talking about, and if we are talking about this particular frequency band, then it is going to directly impact on my interconnections. So in terms of again I'm just talking about the interconnection from the length of my connections. That's that going to affect basically from the performance point of view. Capacitance come into the picture when we are talking about a particular uh, high frequency related thing. Then if you have a long wire, if you have the width related things, like, okay, what is a metal wire, what what is the width of the thing, what that particular wire, the width, spacing, and all those things. So I just capture one formula just to give you an idea, like, okay, the antenna patch width, if we are talking about how it is going to relate with the frequency. So someone just asked, remember someone asked, like, okay, how the metal type of a metal and the frequency, how it is going to relate with each other, and how you're going to decide that particular part. So just to give you an idea, like, okay, this is something uh, depends on the property, the type of dielectric which you are going to use. So all those things has a relationship with the frequencies. So these are different packaging type. You can just note down these terminology, and you can just read it later on, like, okay, what technology we are talking about, what are the different changes are there. So like WLP process, I will just give you a couple of slides just to give you an idea, like, okay, what is the difference and all those things. But here there are two things, with a substrate and a without substrate. In a with substrate, you can see, like, okay, there is a flip chip, we just discussed that particular part. Then there is a interposer also, like, okay, there is a TSV interposer. So what happened, I forget. It slipped from my mind. What is the full form of this TSV? Basically, it's a via. Basically, it's a kind of a via. And what happened? Like, okay, when we are talking about the via, is just like there are two metal, and the way you connect those two metal. So we usually talk about that is a via. via. So metal 1 and metal 2, how those a particular signal, how it's going to transfer from metal 1 to the metal 2, that is through the via. So till now, this via we are talking about, we usually talk about metal 1 to metal 2, metal 3, metal 4, metal 5, like in that particular way. But people were saying like, okay, I gave you an example, like, okay, always we talk about the connection is going to be metal 1 to metal 7, 8, 9, 10, and then at the top you will just come up with a particular wire, like, okay, now it's going to connect with the outside. So just to draw that particular part, maybe that can help you to understand. So what happened if this is my chip, and you are going to fabricate some mosses or some devices here, and after that what is going to happen, you will say like, okay, this is my metal 1, this is my if I will talk about the metal 2, then the metal 3, metal 4. So you will just connect like this, and then the finally you will just come here and you will say like, okay, outside word now is going to connect it. So basically from here, I'm just talking about like, okay, outside word, it is going to connect like this. Come on. Okay, somehow still I'm not comfortable here. So red is here. Where is the pencil tool? Okay, so I was just talking about like, okay, outside word I'm going to connect like this. Now, what people were saying, like, okay, if I have to communicate with the outside world, and let us suppose this device is here, and you are just traveling like this, and then you are just communicating with the outside world, because that's what things are there. Your structure is multiple layers are there, and in that, but man, okay. So this is your structure is there basically, and this structure I'm just talking about. So this is, I'm not sure like, okay, how many of you are able to understand, but the thing which I'm just trying to explain you, like, okay, you can come up with the here only. So this is your outside word. So this is basically the thickness of your chip. Now what people are saying, maybe one of your friend, maybe he came up and he said like, okay, uh, if this is my if this is my substrate, if I have a NMOS here, PMOS here, this is my connection. So why go in an upward direction? It's in the top direction. Why can't I just come here and I just say like, okay, this is, I will just come up with the connection here. Who is saying like, okay, you cannot come up with the connection here? I can come up with the connection here. But the point is, there is a difference. Here we are talking about the dielectric metal and everything. And that's the reason we are talking about the standard process is metal 1, metal 2, metal 3, and metal 4, and then you will just go there. But in the second one, what is happening? You're not talking about going upward. You say like, okay, I this is a nearest one. I can just go from here to here, and I can just connect like this. So in one way, you can also say like, okay, if you have to just go to the America, so there is a one way, you just go in up the sky and just travel and just get down in America. And there is another way, someone say like, okay, I just want to create a tunnel inside the earth, and it's very easy for me just to travel across the that particular tunnel, and I will easily reach in the lesser time. So it's something that particular part, like I know like, okay, it's not the good example, but yes, it's something related to that particular thing. So for that particular portion, to just to give the thing, this TSV come into the picture. This via is there. So it's like basically you will just travel like this and that way. So I just gave you an idea like, okay, what basically how it helps us to save a space, and in this particular way people have worked from the packaging point of view. So these are the things which we are using in the industry. But now in the when it comes to the 5G, when it comes to the future communication, yes. So there are something come up with we come up with a without substrate, which is a WLP process. So here there are the different type of things like, okay, we will just talk about the chip, we will just talk about the different configuration, then the different packaging from the I would say um, from the semiconductor point of view. Yeah, so there are different things how you're going to package the things, how you're going to make a connection from the outside world. One of the things which maybe till now I'm just talking about the what is the WLP process. What is that WLP process? So it's basically the wafer level packaging. So till now, traditional thing is there is a wafer. So in this particular wafer, all the blocks which you're seeing, these are basically all the chips. So usually what happen in a single wafer, we have thousands of chips. So that chips are going to be there. Once the chips are there, then your each individual chip you're going to do the packaging. So that's a traditional thing. So usually we do in this particular way. So wafer, then you're going to dicing in the sense you just cut it into the separate pieces, then you do the packaging. So that's the way the packaging industry work right now. So produce the some particular thing in a mask. So this is like in a mass production, and then just divide it as per the quantity and then do the packaging. But what is happening in the wafer level packaging? That means you're going to change this sequence. What you're saying, this is my wafer. I'm going to do the packaging here itself. Packaging now. Now, now I'm not talking about the packaging in the sense the adding a cardboard or something like the plastic cover or those things. Now I'm going to do a packaging so that within a wafer I can do the packaging. So that obviously within the wafer, if I'm trying to do the packaging, that means I have to change the packaging technique. Now, if I'm going to change the packaging technique, that means the different process is going to be there. That's the reason we were just talking about without substrate and the with substrate we are talking about. Now here itself, you're going to do the packaging, then you're going to cut it. And that's going to help you a lot. And those are the advantage of wafer level packaging. So like here, you will see. So this soldering ball, you can see this one. So this is a part of the wafer itself. So you are going to do it in such a way like, okay, this become a part of a wafer only. Now it's very easy for you just to make a connection in the outside world. Here what will happen, you will just disconnect it and then you're going to connect with the outside world, and then we have all those dies, substrate, flip chip, wire bond, all other things are there. So this is basically the interesting one. If you will if you want to just read it, I think is going to uh, it's going to help you a lot. I know like, okay, it's going to be more deeper in a semiconductor side, but exactly it's not too much in the deeper in the semiconductor side. It's just a packaging part. It will help you a lot to understand a lot of things. Advantage point of view, obviously is going to reduce the size, and it's going to we are going to remove the packaging substrate. Thickness is going to be little lower because now you're going to do the packaging first because everything is in the wafer itself. And foundry can do it as a part of a manufacturing process. So it can be like low cost. You can also, no, I'm not supposed to comment on the costing part, but yes, it's basically along with the foundry IP, the IP which you will take or the amount which you're going to pay, you can just negotiate on that particular part, and enables on wafer testing. So before you cut it, you can just do the on wafer testing also whether everything is good or not. Two things, again, very simplified way. What is the conventional thing? There is a SI chip, there is a RDL layer, then you have the bump metallurgy, and then the solder ball. Now here what we are talking about the this chip is there. When we are talking about the wafer specific thing, then definitely you have to come up with a certain outside with this particular chip, and because this is a something where you're just going to make a cut. So within the wafer you will come up with that particular part, and then rest of the process remains as it is. You can ask me which one is best. Puneet, the first one is best, the second one is best. Answer is in front of you. Depends on you. Don't ask me. So there is nothing like in a best or the worst technology. It depends what is your requirement. You want to save money, you want to save the die size, you want to do a better integration or the electrical performance. So it all depends the design to design, the industry to industry in the sense the company to company, what is their priority. On the basis of that they can choose that particular part, because every process, packaging process, it has on advantage and disadvantage also. Okay, so I think I'm somehow successfully completed my second portion also within a very less time, and the third also I will finish I think before time. So, but yes, if any one of you have any question till this point, try to answer those things without jumping too much into the uh, semiconductor side. So there's a one question, what is the difference between the P cell and the standard cells? So standard cells is AND gate, NAND gate. These are the standard cells. And when we are talking about the P cells, it's basically the very small component, you can say, like I said, PMOS with a particular specific property. Now, when I'm talking about the standard cell, so standard cell, remember, standard cell is more or less related to your the logic gates, which you can use directly as for your from the functionality point of view. But you cannot use a PMOS and you can say like, okay, uh, uh, it's going to it's basically from the functionality point of view, you cannot use that particular part. Yes, what you can do, you can use a different PMOS and create your own AND gate. If you're doing in that particular way, so the use of those pieces come into the picture from that perspective. When I'm talking about the standard cell, that means AND cell AND gate is already there. It is already characterized. So that I can also tell you from the file point of view also. So if you're going to characterize your AND gate, then you will get a .lib file. Like in a .lib file, you will have the characterize the delay related, the power related information of your standard cells. That's basically the standard cell related thing we are talking about. And then you can create a different standard cell, that means different AND gate using a different type of PMOS, different type of NMOS. So in a standard cell library, you will get, if you're getting a, let us suppose 10 different type of AND gate. So basically in a 10 different type of AND gate, maybe you are using only two type of PMOS and a two type of NMOS, but the way you are creating a combination, that is different. So you're going to use those two PMOS, two NMOS in a different combination, and then you just creating a standard that one AND gate, and similarly the standard cell library, and then you're characterizing, and then you're giving it to me, and you're telling me like, okay, Puneet, you can use this AND gate directly. So that means now I don't worry about the PMOS and MOS. So I'm going to use those standard cells directly, and that's the reason that's the standard cell based design. Now you came back and you said like, okay, I don't want to use your AND gate. I want to design my own AND gate. Then I said like, okay, good. So these are the PMOS, these are the NMOS, and when I'm talking about these are the NMOS and these are the PMOS, again, you're not supposed to simulate those NMOS and the PMOS from their functionality point of view, from not the functionality, like from their characteristics point of view. So from the PMOS, okay, what is going to be my thickness, what is going to be my basically the length, or the from the foundry point of view, what is going to be happen. You're not supposed to do that particular part. What you are going to do, you will just use it as it is, whatever the P cell foundry provided you. So when they are going to provide you that particular P cell, they are going to provide you that particular model. That means now they are talking about the foundry specific parameters, gate oxide thickness. So in none of the layout we are talking about the gate oxide thickness. We are not talking about the concentration, doping concentration. We are not talking about all these things, because that is not as a user control, because that's a foundry specific. Now, if that is a foundry specific and foundry is saying, okay, I support 3 type of gate oxide thickness, but none of the tool is a 3D. So you cannot say like, okay, I'm going to change the thickness of my gate oxide, because if you will do it, then there is going to be a one more verification process, like, okay, whether you are following that particular thickness or not. That means again one more DAC will be there, but right now that's not the case. So if I'm saying this is the thickness, and with that particular thickness, with that particular thing, if I will give you everything and that is already simulated and there is a respective model is there, then that means now you have to just use that particular part as it is. So that's a part of a P cell. So using all those P cells, you can create your standard cells. So that's this. I think now you must be clear, like, okay, what is the difference between the P cells and the standard cells? Okay, so here's the one question. So in this package type, do and okay, package type, do you mean substrate as semiconductor substrate or some other substrate? I'm just talking about the PCB related part. Uh, that because when I'm talking about this substrate outside the chip, so I'm just talking about the substrate. That's the reason I was just talking about flip chip, wire bond, and then you will see like, okay, there is a chip is written. So I'm not talking about the substrate of the chip at that particular point. I'm just talking about in the PCB how you're going to connect the connections with the outside world. So that substrate I'm just talking about. Somehow there are a couple of terminology which is common in the PCB designing side and the VLSI side also. Like the substrate is there, then there is something layout also. So yesterday I was just searching for the something for the layout, and they started giving me the PCB layout. So I was like, okay, I'm not looking for this PCB layout, but yeah. So those things are there. Any good reference to read about packaging? I'm new to packaging and never ever studied it before. So Soham, good reference. I think I can suggest you 2 good reference, and uh, both the reference has their own search engine. Search engine and search bar is there. The one is a Google. So you can just go and just search in the Google, and you will get a lot of material. And the second thing is, yeah, I mean, it's a joke apart, but IEEE papers. So you can just there is a I think there is a separate packaging related area journals are there in IEEE. I remember like when I did MTech at that particular time, the packaging related journal were different. And if I'm right, maybe if any one of you can correct me if I'm wrong, but I remember there is a separate packaging related journals are there. So I will suggest you just to do that particular thing. So books and all or the general material if you want to read it from the packaging, then you will not find a lot of articles from the packaging side. But yes, some companies are there. Those are in the packaging industry, I would say, not not the packaging industry of the Amazon and all those things. I'm just talking about semiconductor packaging. So they may have certain articles, but those are again limited to their work. But if you really want to understand and if you really want to read these things, then the IEEE journals are the best one, and they will give you a good amount of knowledge. I think because I think that's something you can just IEEE access. If you can get somewhere, then it's going to be too good. Okay, anyone else? Any other question? Or I think Ashish is quite since long. Maybe we can ask Ashish. Ashish, do you want to add something, or are you there?
Yeah, but I am not able to see question. Which question you are asking?
Yeah. So, but you can add something. So no need to answer any question, but you can add something.
Okay. Basically, what you have told till now is like, I think it like a lot of information already been transferred. So just to add, this is basically if like what I taught you yesterday, the layout thing, that was basically the PCB layout, but those layouts can be made at the wafer level also. So, but all the things we have just told you, the regarding the packaging and all, somebody was asking yesterday that if our design starts radiating, okay, so basically it can act as an antenna also. So basically, these packages help us so that our design, our filter, or maybe amplifier design does not radiate. Okay, so it helps to uh, basically shield them from the other components. Okay, so that's basically the importance of package. Yeah. So rest will go ahead. Okay, so I think 1 hour is left. So you can continue.
Yeah, 1 hour is left, or it's like half an hour, 40 minutes are left. So
Yeah. So
here is
I think you have enough. I think you have enough information to pass on to our participants. So I'll ask to like to continue, but I think there will be a questions from participants. There are very good questions, so you can continue as long as it will be there. So it's not like time bound such thing. But I think these participants have one more lecture at around 3 from Jatana sir. So if you can wrap up quickly also, then it should not be a problem.
oh, so there is a one more lecture after this. It's 3 o'clock, 3 to 4.
Yes, 3 to 4 is one more lecture.
Oh, so if I will just extend it, then I will be the person who's going to just eat their lunch, right?
Lunch, yes, yes, yes. So just make sure don't stretch beyond 2:15. Okay, so
Yeah,
because
yeah, yeah, don't worry. So I'm going to wrap up everything even before time. Don't worry. So like I said, I took a lot of time in a PDK related thing. So now nothing much. The way I finish everyone, I'm just referring to everyone. The way I finish the packaging part, I will just finish this particular topic also. Okay, great, great guys. I didn't know. Like, okay, these people have one more lecture after this. Hmm. And that means it's a long day for these people. Okay, guys. So let's talk about the 5G implementation design challenges. So most of the thing we have discussed, but one of the important thing is, like I have mentioned in the past also. So this millimeter frequencies, millimeter wave frequency which we are talking about, it's not like first time we are using, or we are going to use only in the 5G. There was a couple of past applications also, like satellite communication, military application, radar application. We were using this thing. And why we were using, and because there are multiple reasons. No one is using, and it is not like um, like in the military. I can tell you, basically, from the security point of view, no one was using in a normal communication thing. That's the reason we were using that particular part. But the point was, uh, these communication, these systems, these were the bulky systems, and this is like the power hungry systems are there. So yesterday I was just trying to check the example for this the power hungry related thing. So somewhere it was written like, okay, in a World War II, Japan used this millimeter wave frequency, and that means we are talking about that particular era. Like, so even in that particular time, we use these millimeter wave frequencies, and we know very well. Like, maybe you have seen in the movies and all, the radars, the communication devices at that particular time was very, very big in size. And those are like, the from the power point of view also, it has a lot of circuits and everything. But in a 5G, when we are talking about, we are not talking about that there is going to be one mobile, and along with that you're going to carry two or three power bank, or maybe there is a power solution, like in a size of a laptop. So that's not we are talking about. So you have to solve all that particular thing. You have to think from that particular perspective also. Another thing is the challenges which usually come, that is the propagation related issues. The In terms of the components, if we will talk about like how you're going to design that particular part, then you have to understand like, okay, in a CMOS technology, are we supporting that thing? So if you remember the very first day, and I'm sure like today Jitana sir will also, maybe he will also talk about that particular part, like what are the other processes, what are the other things which we use apart from the CMOS technology. The very first day also, we have a very good presentation on that particular part also. So there are the different technology on which things are working. So these are the challenges, and this is something we have to understand. Just to give an idea about the way the research are going on, and you guys are working. Like when I'm talking about the research community, you guys are working on this particular part. So initially, in a short range, if we are using the remote sensors and everywhere in the car automation, we are just talking about that particular part. Then we also have the IEEE standard like 802.15. All those protocols are there where we are talking about wireless related thing. But now we're talking about the mobile broadband related system. We are talking about the 5G related part. Now there are antennas related thing. Then there are concept, I think Ashish may have covered that particular thing, which I'm not going to cover. Is like, there are the cells. There are the three or four different type of cells are there. When I'm talking about the cells, it's basically the reason. So that reasons are there. Within that particular region, the one frequency band is there. Then you can reuse that particular frequency band in the another cell. And within the cell also, now we are talking about the subcells also, then the P cells also. So those concepts are also there in a advanced, not the advanced, the future communication. Yeah, I like that word, the future communication. So in we are using those things, and that solves a lot of problem when it comes to the 5G related thing. It solves a lot of issues. But couple of issues which I just want to highlight. One is like the EM challenge. If we talk about, so we talked about, obviously this is something you already knew. Like, okay, the challenges usually come from the attenuation point of view, penetration point of view, the reflection point of view, and the main reason is a smaller wavelength. So the the wavelength is going to be very small. And because of this smaller wavelength, if we will talk about the penetration or the diffractions, so these are going to one of the issues I would say. Material penetration diffraction causes more attenuation. Now, if you have a smaller wavelength, then and that is comparable with the particle size, so you can understand like okay, maybe it can completely block your signal itself. And if it is if it's just like so I usually explain this particular part in a very different way. It's like, let us suppose if you have a car and if you have a very small stone, so obviously no one can stop you. You can just hit that particular stone and you will just uh, nothing is going to happen. And nothing is going to happen in the sense, even your car is not going to from the damage point of view also, nothing is going to create any problem in the performance of the car. But if the size of your car is less, or you can say the size of your stone is going to increase. So in our case, what is happening, the size of the car is reducing. That means the wavelength we are talking about, because the car is basically, I'm just talking about a particular signal carrying a particular data. Now what is happening if that small car is going to stuck with that particular particle or that a rock, I would say, if that size is comparable, then things can damage. It can damage your car also. It can damage your signal also, means the passenger basically, or it can also block 100%. So you have to understand from that perspective, like okay, how you're going to solve those things. So few examples like even in the atmospheric gases, water vapors, the rainfalls, that can create a problem. So from the propagation point of view, what is the propagation we are talking about? So we are talking about like okay, in a signal, we just like in a atmosphere, if you will just pass a signal, whether that particular signal will reach at the other point, other side or not. So that's something we are talking about, the signal propagation. Now because of all these things, vapors, rainfall, what is happening, because now these things become comparable to the wavelength. So the penetration, when we are talking about the propagation, it's like few hundred meters. After that, it's going to affect the signal propagation, because the initially maybe because of the power, because of the signal strength, maybe it's not going to hit, it's not going to affect, but after that is going to affect your signal quality or your I would say the accuracy also. Similarly, the trees penetration losses due to the presence of the trees. We are talking about the buildings penetration losses due to the outside buildings, materials, bricks, concrete pillars. Similarly, even in the house itself, we are talking about the wood, glasses, furnitures, everything. So it's not like only the 5G, it happens in the 4G also, it happens in the other 3G, 2G, every where it is happening. But and every time we try to solve this particular part, even today in a 4G, you will see there are a lot of network issue. And that network issue, you will not get that network issue in a I would say in a village. If there is a tower, uh, or I would say if you can see the tower easily, then you will not see that issue until unless it is basically uh, the cell size is increased, the power related things are maybe the issue. But in a where there are a lot of buildings are there, then you can see maybe in one portion of your house, in one corner of your house, the signals are very good. In another corner of your house, the signals are not good. Then why it is? It's not like there is a problem from the Airtel or there is a problem with the Geo. The problem is in terms of your the, the 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 reflection, I would say. The buildings are there, that is a problem. So there is a concept like okay, there are the dead zones, and then in that particular zone, what happened? The two signals from the different phase, they come up and they just cancel each other. There are the signals even after the reflection, all those things, it will never ever reach there. So all those things come into the picture. But 5G, it is, or I would say the millimeter waves, it's more challenging because now the frequency, when you're talking about the wavelength, that become a comparable parameter. So we have to understand that particular thing. Those challenges are there. So for that, now I'm with this particular base. Now I'm just going to talk about certain implementation related challenges in a semiconductor side, like okay, how you're going to design or implement a passive components in a silicon point of view. Like the best one is the inductor. So what happened in case of a inductor? So it's very easy for design a large size of inductor, and it's good. But when we are talking about the large size of inductor, then only I will say like okay, like in a chip, if I'm just talking about if you're going to scale down the things. So if you're going to scale down the things, so as per the theory, large size inductor is required to obtain the desired inductor values. So that's our that's the theory we're talking about. Now, if we are talking about the on-chip inductor, then the poor quality factor, because of what? Because of transmission losses. So we have to think like, okay, how you're going to reduce the transmission losses, how you're going to reduce your radiation losses, how the things are going to conduct. Like if you remember, I was just talking about the substrate related things. Like okay, there is a substrate losses are there. Now those things play a very important role when we are talking about the on-chip inductor. Now, in an on-chip inductor, when we are talking about, then there are the different designs. So what people like you in a MTech or the research scholar, they come up with a different design. They said like, okay, these are what I'm going to do if I have to create a big inductor. What I'm going to do, I will just come up with this particular shape, this particular shape, this particular shape. So just to give you an idea, like, okay, what are the advantage and disadvantage of these shapes, like in a square shape, circular, and the octagonal? Advantage in a square shape is very simple. There are the four sides, easy to design, and it will give you the high value. That's not a problem. The problem is going to be with the low quality factor. The quality factor is going to be different. I think, and that's a portion Ashish can help you out with the formula. Like okay, how the quality factor is going to be the problem here, because these squares are there. So this is something we these are these terms if I will talk about. So this is going to create a big problem. So there are the solution for this particular thing. But yes, that's one of the problem area. So for that, to remove that particular part, or from the inductor point of view, this is the standard one. You can say like okay, the circular implementation, if you can implement it, it is a high quality factor. That is the inductor we are talking about. But yes, how you're going to lay out, how you're going to fabricate this particular part, it's very difficult. But when we are talking about the semiconductor, then if I will say like okay, I'm going to go with this octagonal shape, or there are a couple of other ways also. But yeah, if I will talk about this octagonal shape, so in this octagonal shape, everything is good, but only this, yes, it's a large footprint is going to be there, but that's okay. We know like okay, that's going to happen anyways. Now in the from the design rule point of view, if anyone is going to ask you like okay, Puneet, what is the thing? So in a digital, in a this thing, what is the difference? So uh, what happened here? So first of all, we were just talking about in our semiconductor, like orthogonal shapes, I would say, or perpendicular shapes. Like means there is going to be I would say the um vertical and horizontal. We usually use in that particular way. So I would say the shape supposed to be in a form of 90-degree. So like if something is in X direction and another thing is in Y direction. So you can go with that particular part. It's easy to design. But when we are talking about this thing here, we are talking about the 45-degree. So if the 45-degree is there, then from the layout point of view, that's okay. You can do it. But from the fabrication point of view, in a lower technology node, we have to just check it. Like, okay, what are the rules are there for this 45-degree things? So you cannot say like, okay, whatever the rules for this and this, that's going to be the same for this 45-degree. So that means when I'm talking about the complexity, when I'm talking about the design rule checking point of view, so it's going to be the different design rules, and you have to make sure like, okay, this is working. This 45-degree things are working. In a digital side, if you will talk about, I remember in a 360 or I think 180, 360. Yeah, I think till that time, and even in the 180, 45-degree was allowed. But in the 90 or the 65, we were saying like, okay, 45-degree is not allowed. This is something I'm just talking about from the digital point of view. So you can understand like, okay, whenever we are talking about the scaling, if we are talking about designing something within a semiconductor field with a 45-degree in a lower technology node, then uh, that's not that easy, and that's the reason we are talking about the complexity. That's the one thing. Then there are other thing is like in terms of the optimization related thing, like, okay, how you're going to optimize the value of the inductor, the quality factor. There is again something known as the resonating frequency of the your inductor. So what are those parameters on which these things has a dependency? So you should know that particular part. I just capture a couple of things like in a track width, inner radius, the number of turns, and the track spacing. On the basis of these four things, these are four things are basically the general number I'm talking about. On the basis of these things, you can optimize your layout. From the footprint point of view, also like I have mentioned, there are going to be a large footprint. So just to minimize the footprint on the silicon passive components, so you can just design it as close as possible. But if you will do that particular part, then inductor is okay, but the coupling effects come into the picture. So maybe individually you're okay, but the coupling things come into the picture. Now I took it here the example of the square, but frankly speaking, now as per my understanding, we are not using the square one. We are working on the octagonal. Even if we are using the square, I will. So these corners we have to work on this particular corner. So in the last, I have one slide just to show you like, okay, if you are going to work on the square um, inductor, then you have to make certain changes at these ends. So that's one thing. Then in optimization, there are a couple of other techniques in terms of the shielding, in terms of the stacking, in terms of the nesting. So these are a couple of structures which I've just captured for you just to give you an idea like, okay, how we do it and what are the different things you can do it. Now here, when I'm talking about the stacking, so that doesn't mean you can just stack like in a single wire, this particular way. Obviously, if this is a metal one, this is going to be the metal two, then this is going to be the metal three. So because in our semiconductor, the moment the label changes, the metal name is going to change. But yes, the is basically a type of stacking, and the spiral you're just creating that particular part. Now the next thing is your uh, basically all of you know, like, okay, in terms of the transmission line, and in the transmission line, if you want to design it, if you want to fabricate these transmission lines within the chip, when I'm talking about the within the chip, now this substrate which I'm talking about, this substrate is basically the silicon substrate I'm talking about. Now this substrate is not like I'm just talking about the PCB substrate. But yes, like Ashish mentioned, the PCB related concepts, and even if you're talking about the semiconductor, few of the things are almost similar. So in a PCB also you will study this particular part. Like okay, there are the substrate, there is a ground, there is a micro strip lines are there. You will study that particular thing, and the similar type of structure will be there. But when we are talking about the transmission lines in the CMOS, there are two type of things which I'm sure like and we usually talk about the microstrip line and the coplanar waveguide. Now in a microstrip line, what happened? This is going to be the ground. So if you will see this thing, this is basically a single line. So this one, this portion, this is basically a inside the presentation. You can say it's a long wire, and that wire is there, and this is the ground. So the complete ground is there, then the substrate is there, and we are talking about this particular thing. That means using a two top metal layers for signal propagation and the bottom layer for the ground plane. So this is going to be the ground plane, and this is my the layer which is for the propagation point of view. Now in a coplanar waveguide, what happened? Yes, this is the good one. The signal wire will be there. The ground will be there. Now here also we have one more structure I will show you. But what you will do, you will add this ground lines next to these signal wires also. So that means now you have one ground wire here and the one ground line here, and this is basically your signal wire. So these are the two structure which we are talking about when it comes to the quality factor, when it comes to the QL, the quality factors. So here you can see you can make the changes if you will just make the changes in the spacing between these lines. Here you don't have any control right now because the substrate thickness is fixed and it's fixed by the foundry. But here at least the spacing, if you will change by changing the spacing, you can control that particular part. This is what I was just talking about, the micro step line. So just to understand, like, okay, this is your signal wire, this is the height of your substrate, this is the thickness of your metal wire, this is the ground, this is the dielectric constant. Now, if we will talk in that particular way, so that means if tomorrow, if you will say like, okay, Puneet, how we are going to calculate, how we are going to calculate in terms of means what are those factors on which things are going to has a dependency. So the substrate height, which obviously as a designer you don't have any control. Metal wire thickness, you don't have any control. Width of the metal wire, yes, that's something you have a control. Dielectric constant, you don't have any control. So when I'm saying you don't have any control as a designer, what control you have? You don't have any control in the substrate height, dielectric constant, width of the uh, uh, the thickness of the wire. So you have a control on the width of the wire. So you can just change the width of the wire, and then you can manage. You can just calculate all those things. So that is in your control. Now here also the minimum width, that is not in your control. So every wire has a minimum width. So every wire in the sense, every metal wire, it has a minimum width. So if you are talking about the metal one, metal two, metal three, which metal we are talking about, as per that we can say like, okay, this is my metal, this is my minimum thickness. What you can do here, let us suppose you're saying, look, I will just do it in a metal 2. Can I do it in a metal 2 or metal 3 and metal 4? Because if this is the metal 1, the metal 2 is going to be somewhere here, metal 3 is going to be somewhere here, metal 4 is going to be somewhere here. So you can say like, okay, can I do in that particular part? You can just try and you can see like, okay, what is the performance, what are the other complications, but you have to try that particular part. You have to check it. I would recommend you just go back and just see can that is the advantage or not, because by doing that particular part you are controlling this height. So in place of metal one, if you're just going with the metal two, you're controlling this particular height because now the height is going to increase. And now in this particular area, there are going to be some other dielectric metal, dielectric constant. So that depends on the process, but yes, at least dielectric constants is also going to change. It's like the effective dielectric constants come into the picture. So what you can do, you can just try in that particular way, like, okay, is it going to solve my problem or other complications come into the picture? When we are talking about the limitations, and I just captured two proposed solutions. So limitations is like ground plane is implemented in the close proximity of the signal plane. So like I said, okay, there is a metal one if you are talking about. So very close proximity of the signal plane. I just gave you one idea. Why can't we just do it in the metal 2, metal 3, metal 4? I know like there are the complications, but I'm just talking about like, okay, that can be one of the solution to overcome this particular limitation. But people, obviously, the scientists or the researchers or you guys already tried that particular part. So I just captured this. There are two other proposed solution. One is using with the 55 nanometer by CMOS process. So what they did, uh, they said like, okay, what I'm going to do, the length of the transmission line, we are going to vary using a multiple transistor switches. Because in that particular thing, what happened, the length, how you're going to manage the length. So once you're going to fabricate it, it's fabricated. Now, if tomorrow in your process, if you say like, okay, I want to change the length, can I make something which is a programmable? Can I make something which is a programmable? I want to program it. So now I want to use the length of L. So in some application, I want to use the length of 2L or the 5L. So can I program it? Can I control it from the outside? Or may I supposed to decide everything right now when I'm doing the hardware fabrication? So people came up, they said like, okay, with the help of the transistor switches, we can do that particular part. And so it can change the basically the length of the transmission line. Similarly, they came up with the concept of low loss microstrip line using 130 nanometer BIMOS process technology, and they design it with the additional floating conductor in addition to the signal and the ground plane. So they're saying like, okay, signal and ground plane is okay, but there is something floating conductor. So I will just add one more floating conductor, which is not a signal wire, and that helps them to propose a high impedance and low-loss micro line. So I just capture these two solutions. When I'm saying the propose, in the sense one of the paper, not one of the paper means there are a couple of papers on this particular part, and they propose and they show it like, okay, how it is going to help and solve this particular problem. Now, this when we are talking about CBW, and this is the structure I was just talking about. Now, if you remember in the first slide, I showed you only the signal and the ground and the ground. Here, I'm just talking about one more structure where this is a signal, there is a ground, there is a ground, there is a bottom ground also, and that's the reason I specifically mentioned the bottom ground signal I'm just talking about. It is almost similar. So if you will say like, okay, these two grounds I will remove, it is a basically microstrip line. Yes, it is a microstrip line, but there is a two additional ground wires are there, and these basically help to in terms of optimizing your quality factors. And you can also control that particular part during the fabrication. Means before the fabrication, when you're designing things like, okay, I need this particular quality factor, so you can just change the spacing between these signals. And again, the same factors, it has a dependency over the height, dielectric constant, width, thickness. The fourth one, if you will see, the gap between the trace and the adjacent ground field. So one more factor you have added here. So this is one of the way. I'm just proposing one more thing. Just think about that particular part. So there is a ground, there is a signal, there is a ground, there is a ground. What about after this? There is a dielectric, and then the top also I will have one more ground. So now you can understand there is a signal wire, and around that particular wire there are the grounds. So now in a microstrip there is a one ground. Then we were talking about CPW. Then we are talking about the two more ground like this. Then I said like, okay, with the bottom ground this. What about the top ground? If we will have one more top ground, is it going to help me? If it is going to help me, how it is going to help me? What are the complications are there? So you can just think about that particular part. And just just proposing on the fly. And maybe someone already did that particular part, but at least I haven't captured that thing in my slides, so I can propose anything. So okay, now when I'm talking about the coplanar waveguide CPW, when I'm talking about, then you should know, like, okay, what are the reasons we should use coplanar. So I think we have explained that particular part, like, okay, it's going to give you the better isolation and the better EMI performance. You can control it properly. It has a less crosstalk effects. Okay, but here what is happening? Because everything is once design, everything is design. If that is done, then you will say, like, okay, during the fabrication, there is going to be a quality factor, fixed quality factor I'm talking about. Now, if you want to make it as a variable, then how you're going to make that particular part? So you remember, like in a microstrip line also, we have couple of solutions. You can change, you can have the switches. Similarly, you can also do here, or maybe you can just go with something like someone just suggested this particular solution, like, okay, interdigitize stub, loaded signal line, and the slotted ground shields. So I think you can understand interdigitized stubs, loaded signal lines. So the signal lines you can just digitize some way. You're just doing that particular part, and even you're just creating the slotted ground shields also. Like, okay, that the shielding which you have applied as a ground, you're just also making certain slots. So how you're going to do it, that's a different thing. But yes, that's someone just proposed that particular part. This is the last slide. Then I'm on time, even I'm before time, I would say. And I'm happy, like, okay, the 4 hours I'm able to finish it off. But yes, I just want to show you one nice slide in terms of not the nice slide. I just want to tell you, like, okay, what are the different things you have to make sure when we are talking about the RF traces and when we are talking about the ground planes. So sometimes what happen, we do this type of mistake. We, in the sense, not me, because I'm not working on this particular point. But let us suppose you, maybe you can come up, you can say, like, okay, with this particular way, I want to control the quality, because we were talking about with the help of the space, you can control it. So maybe you will say, like, okay, why can't we just control the space here at this particular place? Some less space, more space, and all those things. No, so that's not the right way to do it. And if it is not the right way, it's obviously the foundry and all other things, maybe they will give you the recommendation, like, okay, you're not supposed to do this particular part. And I am 100% sure Ashish can explain you, or maybe he already explained you that particular part, like why this type of structure is not going to help you a lot. And maybe you already knew that particular part, that this is not the right way in terms of creating any particular structure. So the right way is this. Similarly, I was talking about the band. I was just talking about, like, 90-degree band. You remember the inductor I mentioned, like, okay, a 90-degree band is going to be there. That is not, that's something we usually avoid. Now, if you avoid that particular part, how you're going to do it? So there is something is known as the metering of the right angle turn. So the metering of the right angle turn, what happened? We just cut it. So it's basically it's a square in shape, but if you will see in a micro level, it is basically come as a octonal, like the structure we have discussed, the octagonal shape is similar to that. Because in octagonal, what was the thing? There is no sharp edges. Sharp edges and a sharp turn, I would say. Same thing we are talking about here. The signal, we are just talking about, like, okay, it should not just hit, it will just go like this. And so that's sometime when we are talking about the RF traces. So if you are doing all these things, then you have to just make sure. So here inductor we are talking about. So at least you can just give that particular I would say just reference to that particular part I'm just talking about. Yes, so that's all, and I'm done for the day. I gave you the I finished my task or whatever Ashish and Aditya assigned me, and I hope, I wish things are useful for you guys. But still, if you have any question, please ask. I can see there is two questions. Are transmission line fabricated in the first level? Yes. Second question is, in this inductor implementation tracks specifying are placed horizontally or vertically. Okay, so when you're talking about the horizontal and the vertical, so I'm just going to use a one more terminology because I don't want to confuse you. As such, in VLSI industry, when I'm talking about the horizontal and vertical, so we are talking about usually the x and the y axis, not the z axis. So z axis in the sense the thickness. I'm not going to talk about the thickness. So I'm 100% sure you are not using the vertically means not the 100% sure means I am assuming like okay when you're talking about the vertically you're talking about the z axis. That means the thickness of your chip. And if that is the case, when we are talking about the track spacings are placed between the horizontal or vertical, so we place it horizontal, and you remember there was a one diagram I said stacking of the inductor. So that when I was talking about the stacking, that means now I was just traveling in the width also. So you will just go in the x and the y, and then if you want to go in the z, you just go in the z, and then you will just go in the x and y. So we will do in that particular way. I hope I answered your question. And so there is someone was asking about what is the okay, so someone, okay, I don't know, there are a couple of questions like Q&A for all and the Q&A of my Q&A. Sorry if I missed any question, then maybe I'm really sorry. Why people use CMOS for RF IC? So I would suggest you like maybe you can ask this question to Zatana sir. So because I am I'm sure like he's going to give you the better answer than me. Next is what is the difference in the transmission line inductor implementation with respect to the other on-chip inductor implementation and discussed in the previous slides, and also which one is the advantage of the RF application. So Wasim, I think this is going to be a very long topic of discussion, and uh, maybe if you want to understand this particular topic, don't think from the on chip side. First just try to understand from the off chip, like okay, what is the best uh, way to implement the inductor. And when I'm talking about the line inductor or maybe the inductor with the different sizes, and then see what are the advantage of those things. So I think this whatever be the disadvantage of a inductor in the off chip, same thing is going to be happen here also. So it's almost the same thing, just a matter of at least from the advantage and disadvantage, that's going to help you a lot. How to minimize the parasitic layout? No way, you cannot minimize the parasitic in the layout. So there are a couple of things which you can avoid, like uh, so this basically Aditya, I can answer this thing. Even in the diesel world also, we try to minimize a lot of things, but we are not able to do it. But yes, shielding is one of the things. So the inductor, like I have just mentioned, there the shielding we use it, we just try to cancel the effect of one the other one. Maybe uh, What else? Yeah, that's all. I think apart from that, you cannot minimize the capacitor, because if you will go with the minimum lower dimensions, then you don't have any, you can't control a lot of things. Yes, foundry point of view, they come up with different processes like low K, high K. They usually talk about in that particular way. That means the dielectric constant related things they usually talk about. Uh, what else? Yeah, I think that's the only thing. Apart from that, if you will ask me, it's all about the shielding. How much shielding you can use it. That's the only way you can minimize your parasitics. Okay, for millimeter wave, normal GPDK inductor metal layer one work for the research purpose, how to design reactor for 60 gigahertz application. Suma. So I think ask ashish.com. So Ashish can explain you like, okay, how to design that particular part. Ashish is expert in that. Can you please give a overview about the PDK development flow? Okay. So this question I think you asked two times, PDK development flow. So I'm really sorry. Uh, Maybe sometime else. I had a slide, or maybe you can just search it. Maybe you will find something like, okay, PDK development flow there. Okay, what else? Is there any question remaining? What is the difference? I think I'm done. I'm done almost all the questions, especially for VLSI. Okay, thank you everyone. So Ashish, you want to add something, or you want to close it, or I'm done. I'm done basically.
So I think a very good lecture from you. You have given a like full package to these participants about the PDK development, like how documentation is also important. Then coming to the packaging and the layout issues as well. So I think it was a very good lecture. So and thank you for your efforts. And I would
Thanks a lot,
like
Ashish.
and now I would like if Firoza ma'am can take over, and if any instruction needs to be passed on to participant, so she can give is there.
Yeah,
Yeah,
thank you,
ma'am,
sir.
if you allow, I
Uh,
just want to unshare. Can I unshare screen?
yeah, yes, sir. Sorry, sir. Yeah, so
Okay,
you can unshare this slide, sir. Yeah.
okay, great.
So thank you,
Thank you.
Puneet sir, for such a wonderful lecture. We are getting a very good feedback from the participant, like the insight of the topic was given. They enjoyed the lecture. So thanks a lot, sir, for such a wonderful talk. Gaurav sir could not join due to some academic load. So on behalf of him, I would like to give the vote of thanks to you for giving us such an opportunity. And you delivered it very well, and the participants are really very happy. So we are getting continuous feedback from the participants. So thank you, Puneet sir,
Great.
for such a wonderful talk, sir.
Thank you. Thanks a lot. Thanks, everyone.
So with this, we will be having the break for 45 minutes. We will be joining back at 3 p.m. Today from 3 p.m. we will be having an expert talk by H.S. Jatana sir from HCL Chandigarh. So I request you all to please stay connected. We will start the session by 3 p.m. If you want to disconnect, you may disconnect, but please be connected back by 2:45 so that we can start the event as per the scheduled time. So thank you, sir.
Thanks a lot. Thanks, ma'am.
Thank you, sir.
Bye, Ashish.
Good afternoon, everyone. So we'll start in a short while. So please wait for 2 to 3 minutes. We'll start our session.
Good afternoon, all. We are waiting for all the other participants to join. As soon as all the participants will be joining, we will be starting the event. Thank you. Dear participant, we are starting in few minutes. Please stay connected. Hello, Jatana sir. Hello, Jatana sir. Hello, good afternoon, sir.
Now you are able to see my voice? Hear my
Sir,
voice?
we can hear you. Yes, sir. Yes, sir. We are really sorry, sir, for the technical issue that you faced, sir. We are really sorry, sir.
No, it's okay. This now, yeah, I am sharing this presentation.
Sir, just 1 second, sir. I'm giving you the presenter, right, sir? Sir, now you are the presenter, sir. You can share the slides, sir, right now.
Okay.
Sir, we can see your screen.
Okay, let me open the slides.
Okay, sir.
So are you able to see this?
Yes, sir. We can see your screen, sir. The slides are visible, sir.
Okay. So,
So, with your permission, can we start, sir?
yeah, we will start.
A very good afternoon to the respected coordinators, resource person, and participant. We apologize from our behalf that the session got delayed by 10 minutes due to some technical issue that we faced in Cisco WebEx. We are really sorry for the same. So we are about to start the third session for today. We are very fortunate to have with us Sri H.S. Jatana sir, the senior head of HCL Chandigarh. Sri H.S. Jatana sir received his engineering education from BITS Pilani. He worked at Rockwell Semiconductor USA and AMS Austria for a short duration. Presently, he is working as a group head at HCL ISRO, is a leading team of 80 scientists involved in process development and integration, VLSI design and EO device and product development. His interest area are high voltage MOS process development, SOI, CMOS and BiCMOS process development, radiation hardened device and imaging device. He has more than 10 publications and in IEEE journal and has given numerous talk lectures at various top IITs and MITs. Sir is also associated with us for the last 4 years, and we are really thankful for the wonderful talks and the events sir helped us in organizing. So with this, we would like to invite Jatana sir to please start, sir.
Okay. Thank you, madam. So since this course is on 5G, so what I will be in this one lecture which I have been given 1 hour, so I will be talking about the passive components. For any analog design, you need active and passive components. Now, the passive components are also essential. By passive components, I mean resistor, capacitor, and inductors, which are required, very much required for any analog signal or RF design. So now these passive components have to be fabricated along with the transistors. So the manufacturing process, the fabrication process has to be such that while manufacturing the transistors, you should be able to manufacture these passive components too without affecting the parameters of the transistor. So the screen which you are seeing right now, it's basically a simple cross section of a you can see two metal process, only a two metal process where only two metals are shown, and you see the purpose of showing this is what are the various layers which are used in making these transistors. So starting from the below, there is a substrate, then there are two separate wells. It's a twin well process. So if we start with the P substrate, so in a P sub we have to make two wells. One is N well where P transistor will be made, and there is a P well where N transistor will be made. So now you will ask, what is the difference between P substrate and P well? Both are same. So the difference is in terms of the doping level, the doping concentration, and electrically not isolated. P well and P substrate, electrically they are not isolated. Doping is, if you want to electrically isolate, then what you have to do between P well and P substrate, you have to grow a N layer. So that is deep N well. Why deep? Because that N well is below the P well. Right, so that is known as a D and W layer, deep N well layer. It will electrically isolate the P well and the N well from the P. So both, once it is electrically isolated, both the well, this means all the four terminals of a transistor, including body, gate, source, drain, they can be used, because now the body is not connected to the source. You can have a separate potential. You can have V voltage between source and body, VSV. So you have the flexibility to connect the body to voltage, to any voltage, and, such that any of the PN junctions are not forward biased. So we have a substrate, then we have well layers, then we have active layers, and then we will have contacts and the metals. So now we will see, we will take one element by one element, element by element wise, and just let me go to the next slide. For a simple CMOS process, what are the layers like? Because it is essential to understand these layers. In the sense, we have to fabricate the passive elements. So while designing any mixed signal or an RF circuit, we should be aware of what are the various layers which are used in fabricating those passive or active elements. So if we start with a, for example, a P substrate, then the first mask will be N well mask. So N well mask will define the N well, and other area outside the N well is a P well. Then the next mask will be an active mask or a field mask. Active mask means within N well, some portion of the polygon will be defined as active, which active means where the components will be made, where the transistor will be fabricated. And outside the active region is a field region which is used for isolation. And isolation can be a low cost, local oxidation, or a trench, shallow trench isolation. Normally a trench isolation is used. So in the field area, trench will be formed. Active area will be the area of silicon where transistor will be formed. In both N well as well as P well, it will define the active area. Third and fourth mask, what they are doing is, you see, we have defined an active area, transistor will be formed there. Outside the active area is the field area. So now some of the metal as well as the reverse bias current, because this N plus and P, this is a reverse bias diode. So a reverse current will flow in this diode, in this junction. So this resistor will be leaky. So some current is also flowing to the body from the resistor terminal. This thing will happen in this. So here there will be capacitances to the body. From the resistor, there is a parasitic capacitance which is connected between the resistor and the body. There is a leakage current flowing from the resistance to the body, and there is a temperature coefficient, there is a voltage coefficient of resistor. But if N plus doping is heavier, the depletion width will be small. The value of voltage coefficient, the change in the value of resistance will also be small because the depletion width will be small. So another thing is a very good property of this type of resistance is it exhibits piezoelectric effects. Piezoelectric effects means if there is a pressure applied to this, the value of the resistor changes. So this property is very useful in making sensors, that MEMS device, micro electromechanical pressure sensors. So where a bridge is made and we will make these N plus diffusion resistors, and based on the pressure, the value of these resistors changes. So in a bridge kind of network, we are able to see how much change is there in the resistor, which will reflect to the amount of pressure which is applied. But this is a positive effect. But because of this N plus and P plus junction diode, resistor is sensitive to the variations on the substrate, because you see the substrate is common for the entire circuit. Sitting on the substrate, the transistor is sitting on the, all passive components are sitting on the substrate. The substrate is a common thing, and now this resistor getting connected to the substrate through a capacitor, and because it's a reverse bias diode and there is a leakage, so any signal which is riding on this resistor, it can pass through to the other critical component of the circuit through the substrate. So there will be interference from the resistor to other circuitry and from other circuitry resistor through the substrate. So it is susceptible to interference from other parts of the circuit. So this means noise is coupled to the resistor because of the reverse biased this diode, the capacitance of this, and the noise can get coupled to the resistor from other part of the circuitry. And on is also true. Whatever the voltage is there on the resistor, that can be coupled to the substrate. नीचे कर दी बंद है ना, चलेगा नहीं है, वो भी लैपटॉप भी बंद करना पड़ेगा, मैं कर दूंगा. So the voltage on the resistor 4 बजे तक करिए ना, the voltage on the resistor can also be coupled through other part of the circuitry, so it can affect this. So it's not a, it is this resistor is coupled to the substrate, and through the substrate it can lead to interference with the other part of the circuit. Now if you have to lay out this resistor, so what are the layers you need? You will need, because this is a N plus, so you will need a N plus source drain. Now this white rectangle which are there, I am putting this cursor. So that is a white rectangle outside. So this is the layer. You will have to use this layer. You take this layer in layouting this N plus source drain, and then you active area. So I told the second mask was an active and field mask. So it's an active layer. The blue rectangle you are seeing inside, so this is an active layer, and active will be inside the diffusion N plus. Active won't be outside the diffusion, it will be inside the diffusion layer, and then you will have contact. You are seeing these three small squares, these are the contact on both sides, and then you will put metal on. So what are the layers you need? You need a diffusion layer outside with polygon, then you need an active layer. This is active layer, this is the double. Based on that you will define the resistor, and then you will have these contacts. The contacts, you will have a metal, depending on the design rule you have to give overlays over that should be there in the contact so that the contact is proper. So now, in the same way, as we have N plus diffusion, we can have P plus diffusion also. But what is different here is we are making a P diffusion in N well. You are seeing here N well. In case of a N plus diffusion, we are doing directly N well, N diffusion we did directly on the P substrate. N diffusion resistor, N diffusion we did directly on the P substrate body. But here for a P plus diffusion, we are doing P diffusion on an N well, and N well is sitting on the substrate. So the resistor which is made on the P plus diffusion not directly connected to P substrate, which is the body. So the P plus resistor is not directly connected to the body. So it is electrically isolated from the P substrate. N well as a shield, you can connect a DC voltage at N well. Now you can see here, there will be a P plus N, this reverse biased, and there will be N well and P substrate reverse bias junction. But if you connect N well to a DC potential, this N well you can connect to a DC potential, so then these capacitances, they will not interfere. You can have a very good isolation between this body, which is a substrate, and a P plus diffusion. That is a good electrical isolation is possible. So that is an advantage. So here it is a shielded resistor, but then it will have three terminals. What are three terminals? V1 and V2 are there. Third terminal is not shown, which will be connected to this N well. So you have to give one voltage at N well also, but you have to keep in mind the voltage which DC potential which you are giving at N well, it should not forward bias any of these diodes. And sheet resistivity, in case of N well, here it will be sheet resistivity will be around more than N well, because mobility of holes is 2.53 times like less than the electrons. So there, if here it was 25, 30, 40, so here it will be 80 to 100 ohms per square, and temperature coefficient, voltage coefficient will be similar as the case as was there in N plus diffusion. So these are the two resistors which are formed in the diffusion, quite popular and quite commonly used too. Then let us go to the layout. How we will do the layout? Now the layers which are used in the layout. One is the first is the outer layer you will take, which is N well, because we have found this P diffusion resistor in a N well, right? So we will have N well layer first, our outer. Then within that N well, we will have a P plus source diffusion, which is the next. You can see here is polygon P plus source diffusion, and within the P plus diffusion, we have a this blue rectangle. So three rectangles you are seeing. The outermost is N well. Within N well, we will, which is a P plus rectangle. Within diffusion, we will have an active region. So this active region and the contact on both sides. And this is the length. This is the width. W by L, depending on values of W, define this, the value of this resistance. So this is how you will realize this particular resistor. Now we have covered N plus and P plus. Then we go to the poly. Poly is the poly resistor. They are basically they are made when fabricating the gate, because after doing the gate oxide you deposit silicon, and that is how the gate stack is made. And and the of the gate is not a pure poly, it's a doped poly, and because interconnect also. So undoped poly has a very high resistance. So you will have to dope it to make it a conducting poly, and the doping level can vary, and heat resistivity can also vary from very low 2025 to very high 2 kilo ohm per square or 3 kilo ohm per square is also possible. But this so this poly resistor heat resistance can vary from a lowly doped to highly doped. Lowly doped may be around 2025, medium doped 500 to 500 ohms per square, highly doped, highly ohmic doped, then the highly ohmic poly, which is very lightly doped, will be around 1 kilo ohm to 2 kilo ohm square. Now this another advantage of this poly resistor is sitting on a dielectric, on a field oxide. Right. So when it is sitting on a field oxide, the you can see here the top layer where V1 and V2 are written, that, and below violet colorish sign layer you are seeing dielectric. So it is sitting over a dielectric, silicon dioxide or silicon nitride. So there will not be at the interface of these, there will not be any depletion region. So the voltage coefficient of this resistor is very low, because there is depletion region, or there will be very small depletion region in the poly. It's very small, so that's why it's very low. But there won't be any depletion region in the dielectric. In the poly side, based on the doping level, there will be some. To compare with the case of a N plus diffusion, where both N plus is a silicon area, diffusion area, so diffusion width will be substantially good. So that is why the VCR, voltage coefficient, is more. So the value of the resistor is not affected by the bias voltage. So the value of the resistor, of the poly resistor, is not very much affected by the voltage across the resistor. So that is the advantage. Now the resistivity may vary depending on the grain structure, and it may vary depending from fab to fab and things like that. Another big advantage of this, which is very useful, is from the temperature coefficient point of view. Lightly doped poly, they exhibit negative TCR, and heavily doped poly, they exhibit positive TCR. So which means, so there is a doping level between lightly doped and heavily doped where the TCR will be 0, and those doping level can be found. For example, for a 4000 angstrom and thickness, if the 500 ohm per square poly, so the thickness of the poly is 4000 angstrom, the doping of the poly is such that it gives a sheet resistivity of 500 ohms per square. This is the meaning. It has a TCR of minus 1000 ppm per degree centigrade. So, but for the same 4000 angstrom thick poly, if you have a higher doping of cell, doping is higher, then the sheet resistivity is low. So if it is 70 ohm per square, then its TCR is a 500 ppm. Okay, so in this, for a 4000 angstrom thick poly, if you have a sheet resistivity close to 200 ohm per square, there the TCR is 0. So when the fab will define this poly resistor, which doesn't change with the temperature, which is a very, as you are aware, all resistance change with temperature. So here the advantage is this particular resistor will not change with temperature. So the the process engineers, they will define the thickness of the poly. Here in this case, it's like 4000 angstrom. So 4000 angstrom thick poly, and the doping has to be such that it gives a sheet resistivity of 200 ohms per square, TCR of 0. And as you can see, poly resistor is shielded from the substrate. That is a big advantage. If it is, there is a dielectric setting at the bottom of the poly resistor. So this means there is no capacitance, no interference. There is no parasitic capacitance. So there is no interference to the other part of the circuitry through substrate. There is no leakage current. That is another advantage. So it's a very good, best resistor amongst all the resistors so far we have discussed, quite widely used, and they are used even if you have to realize a very high resistance, say 200 kilo ohms, 500 kilo ohms, so you can have a high ohmic poly resistance. But there is only one disadvantage. That disadvantage is heat dissipation, because this resistor is sandwiched between two dielectric. There is a dielectric at the bottom of this poly layer. There is a dielectric at the top of this poly layer. So it is surrounded by two dielectrics. And so this means the heat dissipation becomes a problem. So if there is some resistor which dissipates a lot of heat, it carries a lot of current, dissipates a lot of heat, so then this is not a perfect candidate. This is very good use for ESD structures, polyfuses, etc. So now, how do we layout? Layout is very simple. You have to choose only one layer, which is a poly layer, which is shown here in blue rectangle. So it's a poly layer. There's only one layer, and you have to make two terminals, V1 and V2. There are contacts on both sides. So that way, it's a very simple. Next we come to the N-well device resistor. So what is this? This is like, now diffusion resistors are different than the well resistors. Diffusion resistors were made in the diffusion implants. Diffusion implants, we say that source drain of source drain of heat transistors. There we are calling them as diffusion. So, and here this is a well. So this resistor is made in well. You are seeing here, this is an N well. If you have to make a resistor in this N well, you make one contact here and you make another contact here. नहीं आप यूज कर लो इसको, लैपटॉप बंद कर लो, आप करना मीटिंग में कर लो, यू कंटिन्यू, मेरा कुछ वहीं रहने देना, मंडे को here this N well, and we will have to make, for a contact we will have to make N plus and N plus, because you cannot put directly any metal on an L, you have, because the contact resistance will be high. So to have a reasonable contact resistance, you have to increase the doping here, or put a silicide or a silicide here, maybe a cobalt or things like that, and then you have to make a contact. Then only you can put a metal. You cannot put metal directly on a silicon. So here you have to change the doping, and then you make two terminals V1 and V2. Now the doping of N-well is always less than the diffusion. If the doping level is less, this means sheet resistivity will always be more as compared to diffusion. It can be 1 to 3 kilo ohm per square. Now if the doping level is less as compared to the diffusion, this means depletion width will be more as compared to diffusion. So if the depletion width will be more, so this means the voltage coefficient will be worse. So as you can see here, the voltage coefficient of this resistor is very high, which is at 10,000. So it's a non-linear, highly resistance with voltage. And with respect to temperature also, because the mobility of the electrons in the well, it changes with the temperature. So there is a temperature coefficient of resistivity that also is quite high, 1000. And so this, but an advantage of this is it can carry huge amount of current. The current will, so there is a well to carry this current. So from V1 to V2, a well is available to carry huge amount of current. So the current carrying capacity is good. Heat dissipation capacity is very good because huge amount huge amount of silicon is used for carrying the current. Huge amount of silicon is used for carrying the current from V1 to V2, so that here the current carrying capacity, the heat dissipation capacity is very good. But what advantages you? The disadvantages is TCR and VCR. That is the only disadvantage. You can realize with high value of resistor, it will not take much of silicon area because you have sheet resistivity is very high. It's a 3 kilo ohms per square. So 3 ohms per square means if you have to realize a resistor, say of 100 kilo ohms. So, for example, to do the easy, if we have to realize a resistor of 300 kilo ohms, so how will we use for this? If I use this, so here the sheet resistivity is 3 kilo square, so which means I have to use 100 squares. Okay, so I have to use 100 squares. Then I will get a complete 300 kilo ohms. How you define square? What should be the dimension of the square? So that if I take, say, one square is, I am defining by, say, 2 micron. So then 100 square means 1 square will be 2 into 2. So 100 means 400 square, 400 micron. 400 micron square area of silicon is needed for this resistor. This way you can calculate the area, the resistance, which will be used, which will be actually utilized on the silicon. So this is a to increase the sheet resistivity. What you can do is you can have a cap of P layer, and on as where poly is shown, so you can have a P plus layer at this, and so this, and then connect it to a because it's a P plus layer, then you have to connect to a negative region so that it is not forward biased. So, and known as a pinch resistor. And what this P plus region here, it will shield the resistor from the top, from the above. It will shield. So there will not be any capacitive coupling from between any interconnect line which is passing above the resistor. There will not be any coupling between this. So it becomes a shield resistor. So it is a shielded from, so that is the advantage. And this also some fabs offer this resistor also, and they call it as a pinch resistor. So N-well, if you have to do, so how to do the layout? So for an N-well thing, what you have to do? You have to take this N-well polygon first, this layer N-well, then you have to take N-well layer first, then there is a source drain, this N plus source drain is also coming, and then you have active region, blue rectangle is coming, then there are contacts. These are the contacts. Now this polygon, almost squarish, which you are saying, is a poly layer. It will not have any effect on the device because it's a the layer. This poly layer is not required. It's only required in case of a pinch resistor. This poly area, in you want to have a pinch resistor, then only you need this. If you have an N-well device, then you can make a resistor in this N-well. In that case, this poly layer is not required. And you can have a field resistor in the same way. The field resistor in the field region, you will take the contacts, the two contacts. In an active device, we have contacts in the active region. That is why the poly was coming. You see here, we are taking the contacts. This is the active region. This is the active region of an N-well. So here, beyond this, this is the field region. So if you take the contact in the field region, one contact here and another contact here of the field region, then you will have a field N-well field device. This is an N-well active device because I have taken the contact where active is there, because that is why the polyna here, the gate of the transistor will be made here. But if I can use this, I will not make a gate here. I will use this region for making a resistor. But in the same way, I can use the field region also to make a resistor here. So the advantage will be that the sheet resistivity will be even higher. It is, you can see 8,000. It is quite high, and here you can see the TCR is also better. VCR voltage coefficient is also better. Uh, VCR will be worse, but the TCR will be slightly 4,000 ppm. It will be slightly better, but it will be a non-linear resistor. Because the well, again, depletion width will vary. Depletion width will be more, so that the VCR is not that good, and VCR will be good only in case of the poly resistor, where the depletion widths are very small. So VCR will be less than 100 ppm. So in this case, the VCR is very high. TCR is also high. So you can see here in the well field, you will have again the N well and the source drain. And now this is the active area of bore. This is active area here. You can see this is the field area. Why we are putting active area? To make contacts. So I have to make active area to make contacts. And here will be trench isolation will be there in this area. So that is why it's a field area. It's a field area, trench isolation will be there. Here doping will come. In the active area you will dope. So by doing a N plus diffusion, you will dope this region. So this region will be doped while you are doing a source drain diffusion of N transistor. At that time, also will be doped. This also will be doped, and finally you will make a contact at these regions. So how to choose a resistor? To choose a resistor, these are the parameters. Value, then area is also important. Linearity is important. Temperature coefficient is important. Voltage coefficient. Current carrying capability is important. Variations in absolute value. Most of these resistors, they can vary by around 10 to 15% of absolute value. So then interference from other components. So these are the criteria of choosing depending how a particular resistor you want to choose. Now in this, this is the, I will show you some of these which we are offering at our fab SCL. These are some of the components which we are offering. They are 1.8 volt transistors, 1.8 and 3.3 volt transistors, 5 volt transistors. IOs are also 1.8 volt, 3.3 volt, 5 volt IOs. We are offering single poly, not double poly. There can be 4 and maximum can be 6 metal layers is possible. So there will be around 20 to 32 masking layer depending on the layer which you are choosing. So there are variety of analog process modules are there. There is a three different types of transistors: standard VT, high VT, and then there is a nominal VT zero. That VT threshold voltage is zero. So those kind of transistor is also there, and then there are different types of capacitors also. That is a metal insulator metal capacitor having different capacitor density, varying from 1 femtofarad per micrometer square to around 2 femtofarad per micrometer square. So those are also possible. and the metal thickness, last metal is thick, it's at 2000 angstrom, and the lower metal, they are around 650 to 850 angstrom, and the top metal 2000 angstrom or a 2 micron thick. So these are the different which are being given, and you can see this kind of a stack, and the metal is not a pure aluminium, it's a 5 metal stack. It's a titanium, titanium nitride, aluminium, copper, then titanium nitride. So this is a stack. Interconnects are stack of these things, and gate is a 30 for 1.8 volt transistors, and these are some of the design rules, like you can have spacing and line and spacing of active area, poly, metal. So these are some of the typical parameters. The ID set nominal 600 microampere per micrometer. For a standard VT and for a high VT will be slightly less, 520. And the FT is around 55 to 65 gigahertz. And then RAM, the standby current is, you can say, 150 picoampere per cell. But if you use a high VT, it will be around 5 picoampere per cell. So it's a, for a low power design, you can use high VT, but then the access time will be affected. These are the different types of devices. As I told you, 1.8 volt, 3.3 volt, native devices, IVT, standard VT. These are the various types of resistors having a different, you can see sheet resistance varying from 1000 kilo ohms per square. This poly 310, 260 also, diffusion 50 and 80 ohms per square also, salicylated poly and diffusion 1 ohm per square. And there is a metal resistor also, which is 40 milliohms per square. You can see this is for use for fuses. So huge variety of resistances are available. Then you have these capacitors, N-well and P-well accumulation capacitors. Capacitor density 9 femtofarad per micrometer square, and then you have a MIM, metal insulator metal, with a density of 1 femtofarad per micrometer square. And then a variety of diodes having a breakdown voltage of maximum 13 volt, they are available. And then BJT devices are also available. They come in 3 sizes, 1.8 volt device and 3.3 volt device. There are vertical both PNP transistors, NPN transistors. Only 1.8 volt device is available. For an NPN and NP, 1.8 and 3.3 volt in 3 different sizes. And NPN, only one different size is available. And for a MOS, there is a range of W and L which you can choose. And then other things, the 5 volt I told, 5 volts are available. So this is one of these tags which you can use. In our case, you can see here, it's a triple well process. There's a P substrate, there's a N well and P well. You are seeing these are the transistors. This is a PMOS, this is an NMOS, and then this is the gate. So this is the contact of a source drain, and this is metal, this is via, and this is passivation like this. So this is how it is. And questions I can, you please ask, I will try to answer this. Hello?
Good afternoon, sir.
Any questions, please ask.
Yes, sir. Sir, the question, sir, does HCL handle any like 90 nm, 65 nm process libraries?
No. Answer. No. We right now it is only 180. Presently it is 180 only.
Okay, thank you, sir. Participant, may I request you to please put your queries in the Q&A section. I will read the queries on your behalf.
Or you can give my email. They can, if there is any query later on, I can respond by email also.
Okay, sure, sir. I will share your email, sir. Indicator is there or not? Sir, why CMOS is always used for RF ICs?
You see, you can use for an RF, you can use gallium arsenide also, but it's expensive. There is an advantage; it will have very high speed. In fact, the circuits which run very fast, more than 5 gigahertz, they are fabricated on a gallium arsenide substrate. But that is expensive. CMOS is cheap. That is the reason. And CMOS can be integrated with logic. RF can be, you can integrate a RF circuit with a logic, with a memory, with a digital circuit. What I mean is, on a same substrate, you can have an RF circuit also, you can have a logic also, you can have a memory also by using CMOS. But if you go for a gallium arsenide, you cannot have a memory, you cannot have a analog circuit there. You will have only RF, and it is expensive also. So overall solution by using CMOS is very cheap. That is the concept of system chip. You can make a complete system on a single chip. You can have analog, RF, everything, and at a very low price, which is not the case in case of gallium arsenide. That is the reason why for the last 10-15 years, even a good example is our mobile phone. You can have a camera also, even you on a CMOS. So that is the reason it's cheap.
Okay, thank you, sir. Mr. Aditya Kumar, I unmuted you. You can please raise your question because I'm not able to understand your question. Yeah, Mr. Aditya Kumar.
Yes, ma'am.
Yeah, please, you can, yeah. Yes, Mr. Aditya Kumar, do you want to ask any question? Because I'm not able to understand your question.
Inductor is available on the library.
Yeah, inductor is there. Inductor is there. Inductor is made by using the top metal which is 20,000 angstrom thick, and you can have a spiral inductor or various layouts are there. And inductor value can be around 8 to 9, at the most 10, 12 nanohenry with a Q of around 7, 8, 9, like that. That is possible by using metal, top
What is
metal.
possible to get the PDK libraries from SCL?
PDK library you can write at our website, and from your college side you can get it. If you
Okay,
have to
sir.
put a request and sign that non-disclosure agreement, you will get it. And the email is there on the SCL website.
Okay, sir.
Thank you, sir. Sir, how many transmission inductor or capacitor are implemented in CMOS technology?
It depends on your design. You can have as many you like.
Okay, thank you, sir. So what is the procedure to get the PDK libraries?
They have to request at an email given at our website, and they will send the NDA form, and they fill the form from the college side, and PDK will be sent to them.
So the next question is, can we expect 90 nm in 2022?
2022 may not be feasible, but it will take 2-3 years, and maybe even a 65 or so is possible in the next, maybe after 3 years or so.
Okay, thank you, sir. Yeah, Mr. Kusuma, we have unmuted you. You can please ask your question.
Sir, good evening. For highway frequency, for 60 gigahertz and more than W band, they are preferring gallium arsenide compared to
Yeah. Agreed. 60 gigahertz you cannot do on silicon.
Yeah, and one
You
more
are
thing from SCL, I have tried for 180 nanometer for UWB design. But the whatever the PDK is available supported for HSpace, not for cadence in environment.
cadence environment spectre. You mean
Spectre
spectre
was
spice?
not supported, but library whatever I have taken from the research lab that supports HSpace. So will
Yeah,
it
it's
support
a
the
spice.
180 nanometer
Spectre
for
is
Spectre?
spectre is also there. You can make a request. Spectre is also there.
Spectre is also there, sir.
Yeah,
But will
but
these
we are
support
using
for
HSpice.
ADS environment? Will it support?
ADS we support for RF. We are doing on ADS through ADS only. ADS cadence RF flow is through ADS only.
Sir, one more thing in India, but already the entire world is going for 22 nanometer and 60, this 45 nanometer technology. But in India, still we are facing struggling lot in 180 nanometer only. Because see, the problem in this India research, because I did my research in RF, MMA frequency for W band, only related to simulation only. Because I cannot able to library due to lack of library support and other things, MOM agreements from TSMC or whatever it may be. Because India is lagging of RF in 20 years. How to
I agree.
overtake at least in the span of 5 years?
I agree with you because the reason is why we don't have 22 nanometer because the money involved is huge. It's around 20 to 30,000 crore rupees is involved, and maybe someday we will have a foundry here.
Okay.
And because the money and as far as your research work, you can try Euro practice. I suggest TSMC will not entertain because it's a commercial fab. They will not. They will
Yes.
charge. They are only to make money, and they will not do anything. They will not. And Euro practice, you can try. They are also giving 65, 45 nanometer for. But again,
No, sir.
you will have to shell out some 5 lakh or 10 lakhs.
Yeah, whatever they are providing GPDKs in 60
Yeah,
nanometer, the problem is we're not working with the inductors. Inductors will not support for 60 gigahertz because we have to, as per specifications, we have to respin and redesign the inductors. Those GPDK inductors are not
that
working.
they
Yeah.
will not get. I agree with you because you see this also you have to keep in mind that some of these foundries, now if you have to design a 60 gigahertz circuit just for research purpose, they will not give you those files because
Yeah,
they
yeah.
can give you those files for the product. They will not give. Yeah,
Sir,
that thing is there.
Sir, hello, sir.
So you have to design your. What I suggest is by taking those, you design your inductor at your end.
Okay.
Yes, sir. For LNA design, inductors will be coming. Okay. So while designing the
Hello, you can design your inductor by using a.
but above 5 gigahertz transmission lines will not support, sir. Hello.
Above 5 gigahertz.
This transmission line is for UWB design. When we go for the design of the entire LNA design, low noise amplifier design, inductors are the part of the design. While designing the inductor, so they will not support, the libraries will not support.
No, the libraries like no. The for designing an LNA, what you need a inductor, you need a transistor, and not only the spice parameter will not do it. If it is more than 1 gigahertz, then you will need that electro thing, that magnetic part also you will need that. Like S parameters also you will need. So you will have to use S-Spice or Spectra will not do that. The magnetic type simulations also you will have to do. So those in S parameters, complete RF modeling, those few of these Euro practice or they may give, they may not give. I don't know. I have no idea about these, but TSMC and all those things they will not give. And inductors, they have designed inductors, but normally those are for commercial products. For research work, normally they don't give because it's a they have spent a lot of money in designing those inductors, standard inductors, so they will not give unless there is some business potential. But what I suggest is you can Euro practice 65 nanometer is there. You can get a PDK from them, and then you can try yourself designing those at your end.
Okay,
PDK
for
they will give you. Euro practice, yeah, for research work, this is what people do. You see, for a research work, they will not give you those standard elements which those Euro practice or any TSMC has designed. They will not give. But you can work. It is a experience for you to designing inductor also. You start from
okay,
there. So that also you
okay,
can do whatever the information they are giving. Based on that information, you try to design these components at your end.
okay, 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 sir. Okay, thank you, sir. Thank you very much.
Thank you. Thank you. Okay, then if there is any other question, you can ask Madam Firoza and she can send me by email. I will respond.
Okay, sure, sir. Sure.
Okay.
Thank you, sir. Sir, there is a last
Thank you.
question. Should I read it or, sir, should I
Okay,
mail
okay.
the?
No, you
Yeah.
can ask.
How do we implement very accurate and identical registers which are used in flash ADCS or R2R ladder DAC?
Yeah, accurate resistors are not possible in any process, in any fab, even TSMC. There can be variation 10 to 15%. So your design, you never use absolute resistor, you will use a ratioed resistor like R1 by R2. So absolute value of the resistor will vary by 15%, but the ratioed resistor will not vary because both resistors will change by the same amount. So the ratio will not change. And then the layout of those resistors is very, very critical. So how to do the layout? It has to be, the orientation has to be same. You start by having a unit resistor, and that unit resistor is getting multiplied in terms of a finger, like you have in a transistor you have various fingers. So like that, it's a layout. Depending on the layout, that way you can have that. But any resistor absolute value will vary. So the standard guideline, design guideline is never used a resistor. Always use a ratioed resistor. Like in you are saying it's a ladder R by 2 R or R by 2. They are the layout. Their variation will not affect because you are using a ratio only. If R1 by R2, R1 changes by 10%, R2 changes by 10%, the ratio doesn't change. Right? But then the layout is very important. How you are doing the layout. That is important. So for the layout, you see that there are some 2 3 good books. Art of Analog Layout is there by Warren Hastings and things like that. So layout is important, or we can have another lecture on a layout of these components. How to make good layouts. Analog layout, mixed signal layout.
Okay, thank you, sir. Dear participant, yeah, we have given the email ID of Jatana sir also in the Q&A section. So you may drop questions also to sir, or you can drop question to E&ICT Academy also. We will pass the question to sir. So thank you, Jatana sir, for such a wonderful talk. All the participants really enjoyed, and we are getting a very good response from the participant. On behalf of E&ICT Academy, IIT Guwahati, and MNIT Jaipur, and all the participants, sir, we thank you for such a wonderful talk, sir.
Thank you, madam. Thank you.
Thank you, sir. Dear participants, you all may get disconnected. We will be closing the event link in 2 minutes. Tomorrow there will be no class for tomorrow, and day after tomorrow, we will be having the class on Monday. Chaitanya sir, you may stop sharing the screen.